Hello there and welcome to Just About Earth, where curiosity gets comfortable and science takes the long, gentle road toward rest. Tonight, we're setting our gaze far beyond the pace of daily life and into a story that unfolds so slowly it makes even mountains seem impatient. The topic waiting for us is the idea that the world beneath your feet was once a single vast land, a place where there were no familiar oceans to separate continents, no distant shores, and no clear edges to the map. Instead, there was one enormous connected surface stretching across the face of the planet, shaped by forces so steady and quiet that they still move today without asking for our attention. Before we begin drifting into that deep time journey, I want to ask something simple and personal. Where are you listening from right now? Is it late evening, early morning, or somewhere in between? Maybe the room is dark except for the glow of a screen, or perhaps there is a soft light nearby and the quiet hum of the world outside your window. Wherever you are, this moment belongs to you. And if you find this slow walk through science calming or interesting, a small gesture like liking the video or subscribing helps this quiet space reach others who might be looking for a peaceful way to end their day. Now, let us ease into the question that brought us here. How did Pangea really form? It is a simple phrase, but behind it sits a story that stretches back hundreds of millions of years, long before the first human thought to draw a map or name a sea. The idea that all of today's continents were once joined together might sound like something pulled from a dream or a children's book, but it is grounded in careful observation, patient measurement, and a deep curiosity about the planet itself. The ground beneath your shoes, the rocks along a shoreline, and the shape of the land on the other side of the world all carry pieces of that story, even if they never announce it out loud. At first glance, Earth seems solid and reliable, a place where things stay put. Cities rise, forests grow, and rivers carve their paths, but the broad outline of the continents feels fixed, as if the planet settled into its shape long ago and decided to keep it. Yet that sense of stillness is more like a polite illusion. Beneath the surface, far below the soil and stone we see, the planet is restless. It is not rushing, not jerking or shaking without reason, but slowly, steadily, moving in ways that only become obvious when you compare one era of the world to another across enormous spans of time. To understand how a single landmass could form, we need to imagine the planet not as a finished sculpture, but as an ongoing process. Earth is built in layers, like a complex machine wrapped inside a shell of rock and water. At the centre, there is a core so hot and dense that it shapes the magnetic field, and helps protect the surface from the worst of space's radiation. Around that, there is a thick, slowly flowing layer called the mantle. This is not liquid in the way water is, but it is not rigid like a solid block of stone either. Over very long periods it can move, stretch and circulate, carrying heat from the depths toward the surface. Floating on top of this moving mantle is the crust, broken into large pieces known as tectonic plates. These plates are the true travellers of the story. Each one carries a continent, an ocean floor, or a mix of both. They do not glide smoothly like skates on ice, but they do shift, press, pull apart, and slide past one another at rates that often measure only a few centimetres per year. That is about as fast as your fingernails grow. In a single human lifetime, the movement is almost impossible to notice. Over tens of millions of years, however, those tiny steps add up to journeys that can reshape the face of the planet. Long before the name Pangea was ever spoken, the pieces of the world were already on the move. The continents we recognise today were once part of smaller landmasses, themselves assembled from even older fragments. The planet has a long habit of gathering and scattering its surface, pulling pieces together and then easing them apart again in a cycle that repeats over hundreds of millions of years. Pangea was not the first time this happened, and it was not the last, but it remains the most famous because its outline can still be traced in the shapes of today's continents. like a puzzle that was taken apart but never completely forgotten. If you look at a map of the world, you might notice how the eastern edge of South America seems to fit neatly against the western edge of Africa. It is not a perfect match, but it is close enough to make people wonder if that is more than coincidence. That simple observation was one of the sparks that eventually led scientists to take the idea of a united world seriously. But the real story goes deeper than the outlines of coastlines. It reaches into the layers of rock, the patterns of ancient fossils, and the traces of climates that once existed where they no longer make sense. Imagine standing in a desert and finding the fossil of a plant that could only have grown in a warm, wet environment, or climbing a mountain and discovering evidence that it was once part of a shallow sea. These kinds of clues are scattered across the continents, and when scientists began comparing notes across oceans and borders, a strange picture started to emerge. Similar rock formations appeared in places now separated by thousands of kilometres of water. Fossils of the same ancient species showed up on different continents, as if those creatures had once walked freely across land that no longer exists. These patterns suggested that the world had not always been divided the way it is now. Instead, it hinted at a time when land stretched continuously across regions that are now far apart. The question then became not just whether Pangea existed, but how something so massive could come together in the first place. The process begins with the motion of tectonic plates. Some plates move toward each other, driven by the slow circulation of heat within the mantle. When they collide, the edges crumple and fold, pushing up mountain ranges. This is how some of the world's tallest peaks came into being. The Himalayas, for example, are still rising today as the Indian plate continues to press into the Eurasian plate. Over millions of years, these collisions can weld continents together, turning separate land masses into a single, larger one. At the same time, other parts of the planet are pulling apart. Where plates move away from each other, magma rises from below and cools to form new crust. This process creates mid-ocean ridges, long underwater mountain chains that mark the birthplaces of new seafloor. As fresh crust forms, it pushes older crust aside, gradually widening oceans and changing the shape of continents. The formation of Pangea involved both of these motions working in different places at different times. Several smaller continents and land fragments drifted slowly toward each other, guided by the invisible hands of plate movement. As they met, oceans between them closed, and the seafloor was pushed down into the mantle in a process known as subduction. This recycling of old crust made room for the land masses to join, piece by piece, until a vast, continuous stretch of land spanned much of the planet. This was not a sudden event. There was no single moment when the world snapped together like the final piece of a puzzle. Instead, it was a long sequence of meetings and mergers spread across tens of millions of years. Regions that are now distant neighbours were once close companions, sharing climates, rivers, and ecosystems. Forests grew across areas that would one day be separated by entire oceans. Animals wandered across plains that no longer exist, unaware that the ground beneath them was part of a slow global dance. While all of this was happening, the climate of the planet was also shifting. A supercontinent changes the way air and water move around the globe. With so much land grouped together, the interior regions of Pangea were far from the moderating influence of the oceans. This likely led to more extreme temperatures, with hot summers and cold winters, and large dry areas where rain struggled to reach. Along the edges, where the land met the surrounding ocean, conditions were different, shaped by currents and coastal winds. These environmental differences influenced the kinds of life that could thrive in different parts of the supercontinent. Plants and animals adapted to a wide range of conditions, and their remains became part of the fossil record that scientists study today. By tracing where these fossils are found and how old they are, researchers can piece together not just where the continents were, but how the living world responded to their movement. The evidence for Pangea did not come together all at once. For a long time, the idea that continents could move at all was considered unlikely. The prevailing thought was that the land was fixed and that similarities between distant places had to be explained in other ways, such as land bridges that sank into the sea or parallel evolution. It took persistence and a growing collection of data to shift that view. One of the key figures in this story was a German scientist named Alfred Wegener. In the early 20th century, he proposed that the continents had once been joined and had drifted apart over time. He pointed to the matching coastlines, the shared fossils, and the continuity of rock layers as evidence. His idea, known as continental drift, was met with skepticism. Critics asked how solid land could possibly plough through solid seafloor. Wegener did not have a clear answer, and for decades his hypothesis remained on the edges of mainstream science. It was not until the mid-20th century, with the development of new technologies and the study of the ocean floor, that the mechanism behind continental movement became clear. Scientists discovered the mid-ocean ridges and the patterns of magnetic stripes in the seafloor, which recorded the history of Earth's magnetic field as new crust formed. These findings provided strong support for the idea of seafloor spreading and plate tectonics, offering the missing explanation for how continents could move. With this framework in place, the formation of Pangea could be understood not as a strange exception, but as a natural outcome of the planet's ongoing behaviour. Plates move, collide and separate. Oceans open and close. Continents gather and scatter. Pangea was one chapter in a much longer cycle, one that stretches back to the earliest days of Earth's solid surface and continues into the distant future. If you were able to watch this process in fast motion, it would look like a slow, deliberate dance. Land masses would drift across the globe, brushing past each other, sometimes locking together, sometimes pulling away. Mountain ranges would rise and erode. Seas would appear and vanish. Over time, familiar shapes would form and then fade, replaced by new arrangements that no human has ever seen. Thinking about this can change the way you see a simple map. The lines that separate countries and the colours that mark different regions feel permanent, but they sit on top of something far more fluid. The continents themselves are temporary guests in their current positions, and given enough time, they will move on to new configurations. The Atlantic Ocean, which now separates the Americas from Europe and Africa, is slowly widening. The Pacific, on the other hand, is shrinking as its seafloor is pushed down into the mantle along its edges. These trends hint at what the world might look like tens or hundreds of millions of years from now. For now, though, our focus remains on the past and on how Pangea came to be. The story is not just about rocks and plates, but about the way humans learn to read the planet's history. It is about noticing small details, asking large questions, and being willing to reconsider long-held beliefs in the face of new evidence. It is a reminder that even something as seemingly solid as the ground beneath us has a story, one that is still being written. As you let these ideas settle, imagine the world not as a collection of separate places, but as a single, connected surface, slowly reshaped by forces that never truly stop. Picture rivers that once flowed across land that is now ocean, and forests that grew where deserts might exist today. This way of seeing the planet invites a kind of quiet curiosity, a sense that every stone and shoreline carries a memory of a world that no longer exists in the same form. Long before the idea of a single, united world ever took shape, the planet was already busy arranging and rearranging its surface in ways that would one day make that union possible. If you could step back far enough in time, past the familiar outlines of continents and oceans, past even the earliest traces of complex life, you would find a version of Earth that feels both foreign and strangely familiar. The same planet, the same gravity, the same cycle of day and night, but a surface that looks like it belongs to another world entirely. In those distant ages, the land was not gathered into one great mass. Instead, it existed as a scattered collection of fragments, each moving slowly across a restless foundation. These early landmasses were shaped by forces that had been at work since the planet first cooled enough for solid rock to form. Heat from deep within the Earth rose toward the surface, setting the mantle into motion. That motion, slow and steady, carried the crust along like a raft on a thick, flowing sea of stone. The earliest continents were not the wide, stable platforms we recognise today. They were smaller, more fragile and constantly changing. Some were built from volcanic arcs, chains of islands that formed where one piece of crust slid beneath another and melted, sending magma upward. Over time, these arcs collided with other land fragments, welding themselves together into larger bodies. Others grew as molten rock rose and cooled, adding layer upon layer to the edges of existing land. Each addition was a quiet, patient act, measured not in years or centuries, but in millions of years. During this long prelude to Pangea, the planet went through several cycles of assembly and separation. Scientists have found evidence of earlier supercontinents, ancient gatherings of land that formed and then broke apart long before the one we are focusing on. Names like Rodinia and Gondwana appear in the scientific record, each representing a different arrangement of Earth's surface at a different time. These earlier unions remind us that Pangea was part of a repeating pattern, rather than a one-time event. To picture this era, it helps to imagine a map that never stays still. Coastlines shift, seas open and close, and the distance between once neighbouring lands slowly grows or shrinks. A shallow ocean might widen into a vast basin, while another narrows until the land on either side finally meets. When that happens, the collision can be dramatic in geological terms. Rock layers buckle and fold, pushing upward to form mountain ranges that can stretch for thousands of kilometres. These ranges are not just piles of stone. They're records of ancient meetings, written in layers that geologists learn to read like a long, complex book. The atmosphere and oceans during this time were also changing. Early in Earth's history, the air held far less oxygen than it does now. Life, mostly in the form of simple organisms, lived in the oceans and left behind chemical traces in the rocks. Over time, photosynthetic life began to alter the composition of the atmosphere, slowly increasing the amount of oxygen. This shift had a profound impact on the planet, paving the way for more complex life forms and changing how minerals formed and weathered on the surface. The oceans themselves were shaped by the arrangement of the continents. When land is spread out, water can circulate more freely around the globe. Currents carry heat from the equator toward the poles and cold water back toward warmer regions, helping to moderate the planet's climate. When land begins to cluster together, those pathways can be disrupted. Seas can become enclosed, and currents can be redirected or weakened. Even before Pangea fully formed, the gradual gathering of continents began to influence global patterns of temperature and rainfall. Life responded to these shifts in subtle and not so subtle ways. Marine organisms adapted to changing coastlines and water chemistry. On land, early plants began to spread across the surface, stabilizing soils and creating new habitats. Their roots helped hold the ground in place, reducing erosion and allowing rivers to carve more stable channels. These changes, in turn, affected how sediments were deposited, creating rock layers that still hold clues to the environments of that time. One of the most remarkable aspects of this period is how much of it can still be traced today. The rocks beneath modern cities, forests and deserts often contain minerals and structures that formed in these ancient settings. By studying their composition and arrangement, scientists can reconstruct the conditions under which they formed. A layer of sandstone might point to an ancient beach or riverbed. A band of volcanic rock can mark the site of an old rift, where the crust pulled apart and magma rose to fill the gap. As continents drifted, they carried these records with them. A mountain belt that began as a coastal range on one landmass might end up thousands of kilometers inland on another after a series of collisions and separations. This is why similar rock formations can appear in places now separated by oceans. They are pieces of the same ancient story, carried to new positions by the slow movement of the plates. The idea that land could move at all was once difficult to accept. After all, the ground beneath our feet feels solid and permanent. But when you look at the evidence left behind from this early period, the sense of motion becomes hard to ignore. Patterns emerge that only make sense if the pieces of the world were once closer together and then slowly drifted apart. Consider the distribution of certain fossils. Some ancient plants and animals appear in the rock records of multiple continents, even though those continents are now far apart and separated by wide oceans. These organisms were not capable of crossing such distances on their own. Their presence in different places suggests that the land itself was once connected, allowing them to spread across a continuous surface. The same is true for certain types of rock. Mountain ranges in different parts of the world sometimes share the same age, structure, and composition, as if they were once part of a single, continuous chain. When you line up these features on a map and imagine the continents sliding back into different positions, the pieces begin to fit together in a way that is difficult to dismiss. All of this points to a world in motion, even before the final assembly of Pangea. The stage was being set by countless small shifts, each one nudging the continents a little closer or a little farther apart. Over time, these movements created a pattern of convergence, where several major landmasses began to drift toward a common region. This convergence did not happen in a straight line. Plates can change direction over time, influenced by the push of new crust forming at ridges and the pull of old crust sinking at subduction zones. The result is a complex dance, with pieces rotating, colliding, and sliding past each other. In some areas, land was squeezed together and thickened, forming high plateaus. In others, it was stretched and thinned, creating rift valleys that would later fill with water and become new seas. One of the defining features of this pre-Pangea world was the presence of long, narrow oceans that opened and closed as the continents shifted. These bodies of water, known as seaways, played a major role in shaping both climate and life. They acted as corridors for marine species, allowing them to spread into new regions. At the same time, they influenced how heat and nutrients were distributed across the planet. When a seaway began to close, the changes could be dramatic. As the gap narrowed, water circulation patterns shifted, sometimes leading to changes in temperature and salinity. These environmental shifts could put pressure on existing ecosystems, favouring some species over others and driving evolutionary change. In this way, the movement of the continents and the formation of Pangea were closely linked to the history of life itself. The land during this time was also shaped by the work of water and air. Rain fell on the surface, collecting in streams and rivers that carried sediments toward the sea. Wind moved sand across open plains, building dunes that could later be preserved in stone. These processes might seem small compared to the movement of tectonic plates, but over long periods, they played a major role in sculpting the surface of the land. Volcanoes added another layer to the picture. Where plates met or pulled apart, magma could rise to the surface, creating new land and releasing gases into the atmosphere. These eruptions could influence climate, sometimes cooling the planet by sending ash and particles into the air that reflected sunlight. Over time, the volcanic rocks they left behind became part of the growing continental crust. As the continents drifted, they also passed through different climate zones. A landmass that began near the equator might slowly move toward the poles, experiencing a gradual shift from warm, tropical conditions to cooler, more temperate ones. The plants and animals living there had to adapt or move, adding another layer of change to the evolving world. Through all of this, the slow approach of the major land masses continued. What would eventually become the core of Pangea was taking shape, not as a single, sudden event, but as a long series of encounters. Each collision added a new piece to the growing whole. Each closed ocean removed a stretch of water from the map and replaced it with a line of mountains or a broad plateau. The pace of this process can be hard to grasp. Human history spans a few thousand years. The formation of Pangea unfolded over hundreds of millions. To put that in perspective, if you compress the entire history of Earth into a single day, The time between the first movement toward Pangea and its full formation would take up hours, not minutes. It is a reminder that the planet operates on a schedule very different from our own. Even so, the effects of these ancient movements are still with us. The distribution of mineral resources, the location of mountain ranges, and the shape of coastlines all carry the imprint of this long prelude. The ground beneath a modern city might once have been part of a tropical coastline, a desert interior, or the floor of a shallow sea, depending on where the continent was at the time. As scientists continue to study this period, they use a combination of tools to refine the picture. Radiometric dating allows them to determine the age of rocks with remarkable precision. Satellite measurements track the current movement of plates, offering clues about the forces that have been at work for millions of years. Computer models simulate past configurations of the continents, testing different scenarios to see which best matches the evidence found in the field. These methods do not provide a single, fixed image of the past. Instead, they create a range of possibilities, each one narrowing as more data becomes available. The story of how the world was arranged before Pangea is still being written, shaped by new discoveries and new ways of looking at old evidence. What emerges from all of this is a sense of continuity. The Earth we see today is not a finished product, but a moment in a long sequence. The scattered continents of the distant past, the united landmass of Pangea, and the separated world of the present are all different expressions of the same underlying process. Plates move, land shifts, and the surface of the planet is constantly being renewed. It can change the way you think about place. The spot where you're sitting or lying down has not always been where it is now, and it will not always stay here. Over vast stretches of time, it may travel across the globe, passing through different climates and environments, becoming part of different arrangements of land and sea. With that in mind, the world before Pangea feels less like a distant, unreachable past, and more like an earlier scene in a long, unfolding narrative. Even when everything around you feels still, when the air is quiet and the ground seems as solid as anything could possibly be, the planet is moving. It is not the kind of movement you can sense with your body or catch out of the corner of your eye. There is no steady hum, no visible drift of the horizon. Yet beneath that calm surface, Earth is constantly in motion, reshaping itself in ways that only become obvious when you look across spans of time far longer than any human life. To understand how this slow, persistent movement helped bring Pangea into being, it helps to start deep below your feet, far past soil, roots, and bedrock, into a realm of heat and pressure that feels more like the inside of a furnace than a place we usually think of as part of the ground. At the centre of the planet lies a core made mostly of iron and nickel, so hot that temperatures rival the surface of the sun. Surrounding that is a thick layer known as the mantle, a vast region of solid rock that, under immense heat and pressure, behaves in ways that blur the line between solid and fluid. The mantle does not slosh or swirl like water in a pot, but over millions of years it can flow, rise, and sink. Hot material from deep within slowly moves upward as it becomes less dense, while cooler material near the surface sinks back down. This creates broad, slow-moving convection currents, similar in principle to the way warm air rises and cool air falls in a room, but on a planetary scale and at a pace that would make even the most patient observer feel rushed by comparison. Resting on top of this moving mantle is the crust, broken into a patchwork of enormous slabs known as tectonic plates. These plates vary in size, from giants that span entire oceans and continents to smaller fragments that still carry their own complex histories. They fit together like a rough mosaic, with cracks and seams marking their boundaries. Along those boundaries, most of the planet's dramatic geological events take place. Some plates pull away from each other. Where this happens, molten rock from below rises to fill the gap, cooling and hardening into new crust. Over time, this process builds long underwater mountain chains, known as mid-ocean ridges, that snake across the seafloor like the seams of a slowly expanding sphere. The Atlantic Ocean, for example, is still widening today because of this steady creation of new crust along its central ridge. In other places, plates push toward each other. When an oceanic plate, which is thinner and denser, meets a continental plate, it often sinks beneath it in a process called subduction. As the descending plate dives into the hotter regions of the mantle, it begins to melt, generating magma that can rise to the surface and feed volcanoes. This is why many of the world's most active volcanic regions lie along the edges of tectonic plates. When two continental plates collide, neither one is dense enough to easily sink beneath the other. Instead, their edges crumple and fold, thickening the crust and pushing it upward to form vast mountain ranges. The Himalayas, still rising today, are a visible reminder of this kind of collision. Over millions of years, these towering features can be worn down by wind, water, and ice, their material carried away to form plains and sedimentary layers elsewhere. These three types of plate interactions, spreading, subduction, and collision, form the basic rhythm of the planet's surface. They are the reason continents move, oceans open and close, and landscapes change shape. They're also the quiet, persistent drivers behind the assembly of supercontinents like Pangea. It can be tempting to imagine tectonic plates as rigid blocks sliding neatly across a smooth surface, but the reality is more complex. Plates can bend, stretch, and even break apart. Their edges are rarely simple lines. Instead, they form broad zones of deformation, where the crust is fractured, folded, and transformed in many different ways. Earthquakes often occur in these regions, releasing built-up stress as the plates adjust to each other's movements. All of this motion is fueled by the planet's internal heat, much of which comes from radioactive decay in the mantle and core. This heat has been gradually escaping since the Earth first formed, and as long as there is enough of it to keep the mantle moving, the plates will continue their slow journeys. In that sense, the planet's movement is a kind of long, slow cooling process, with each shift and collision a small step in the release of ancient energy. During the time leading up to the formation of Pangea, the pattern of plate motion began to favour convergence in certain regions. Several large landmasses, carried by their respective plates, drifted toward one another over tens of millions of years. Oceans between them narrowed as seafloor was consumed at subduction zones. Island chains and volcanic arcs marked the boundaries where one plate slipped beneath another, tracing the outlines of closing seas. This convergence was not perfectly symmetrical. Some plates moved faster than others, some rotated slightly as they travelled. The result was a series of complex encounters, where land masses met at angles, slid past each other for a time, and then finally locked together. Each of these interactions left behind a record in the rocks, a kind of geological fingerprint that scientists can study today. One way researchers track ancient plate movements is by examining the magnetic properties of rocks. When molten rock cools and solidifies, tiny minerals within it align themselves with the Earth's magnetic field. Because the planet's magnetic field has changed direction many times over its history, these alignments form a pattern like stripes in the rock. By studying these patterns, scientists can determine where a piece of crust was located when it formed and how it has moved since. Another tool comes from the study of rock types and structures. Certain kinds of rocks form only under specific conditions of pressure, temperature, and environment. Finding those rocks in unexpected places can reveal past positions of continents and the nature of the boundaries between plates. For example, rocks that form deep in the roots of the mountain ranges might later be found at the surface, indicating that the mountains above them have been eroded away over time. The movement of plates also influences the shape and depth of the oceans. As new crust forms at ridges, it is hot and buoyant, sitting higher than older, cooler crust. As it moves away from the ridge and cools, it becomes denser and sinks, deepening the ocean basin above it. This process affects sea levels and the extent of shallow seas that can spread across continental edges. During the periods when continents were drawing closer together on the way to forming Pangea, many of these shallow seas were gradually eliminated. Coastal regions that had once been underwater were lifted or drained as landmasses collided and the seafloor between them disappeared. This created new land bridges and expanded the areas where plants and animals could move and interact. At the same time, the growth of mountain ranges altered weather patterns. High terrain can block the flow of air, forcing it to rise and cool, which often leads to increased rainfall on one side and drier conditions on the other. Over long periods, these effects can shape entire regions, influencing where forests, deserts, and grasslands develop. Rivers responded to these changes as well. As land was uplifted, streams and rivers cut deeper into the surface, carving valleys and carrying sediments toward lower areas. Where land subsided or seas advanced, sediments accumulated in layers that would later harden into rock. These layers now serve as a timeline of environmental conditions, preserving evidence of ancient climates, ecosystems, and geological events. While all of this was happening, the plates themselves were not moving in isolation. Their motion was part of a global system, where changes in one area could influence behavior in another. The opening of a new ocean basin could alter the balance of forces acting on neighbouring plates, changing their direction or speed. The closure of an old ocean could redirect mantle flow beneath the surface, affecting where heat rose and where plates were more likely to break apart in the future. This interconnectedness is one of the reasons the planet's surface has a kind of long-term memory. Events that happened hundreds of millions of years ago can leave traces that influence what happens much later. A weakened zone in the crust, created by an ancient collision, might become the site of a future rift. A thickened piece of continental crust might resist being pulled apart, shaping the path of a new ocean. In the lead-up to Pangea, these inherited features played an important role. Some of the land masses that eventually joined together had collided before in earlier configurations, leaving behind belts of deformed rock and structural weaknesses. When the plates began to move again, those same zones often guided the next phase of motion, like faint lines on a page that help you trace a new drawing. It's also worth remembering that the planet's movement is not perfectly smooth. There are periods when plates seem to drift more slowly, and times when motion appears to speed up. These changes can be influenced by variations in mantle flow, differences in plate size and shape, and the balance between the forces pushing plates apart at ridges and pulling them down at subduction zones. During some intervals, the overall pattern of motion can favour the assembly of a supercontinent. When many plates are drawn toward a common region, collisions become more frequent, and large land masses begin to form. At other times, the pattern shifts, and forces that favour rifting and separation become more dominant, leading to the breakup of those large land masses into smaller pieces once again. This back and forth between assembly and dispersal is sometimes described as the supercontinent cycle. It is a long-term rhythm in Earth's history, with each cycle taking several 100 million years to complete. Pangea represents one of the most recent peaks of this cycle, a moment when much of the planet's continental crust was gathered into a single, sprawling configuration. Seeing the planet in this way can be a strange experience. The ground beneath you becomes less of a fixed foundation and more of a slow traveller, carried along by forces that operate far beyond everyday awareness. The place you call home has its own journey, one that began long before any human presence and will continue long after. If you imagine tracing that journey on a map, you might follow a path that loops and curves across the globe, crossing climates and oceans that no longer exist. You might pass through regions that were once deep beneath the sea, or high in mountain ranges that have since been worn down to rolling hills. Each stage of that path would reflect a different chapter in the planet's long story of movement. This perspective can also change how you think about natural hazards. Earthquakes, volcanic eruptions, and the slow rise of mountains are not random acts. They are expressions of the same processes that have been shaping the planet for billions of years. The same plate boundaries that once guided the formation of ancient supercontinents are often the places where the most dramatic events happen today. Yet for all their power, these processes are remarkably patient. They do not rush. They do not pause for human schedules. They operate on timescales that stretch beyond our usual sense of past and future. This can make them easy to overlook, even as they quietly transform the world. As the continents continued their slow approach toward one another in the time before Pangea fully formed, the planet's surface became a patchwork of active boundaries and evolving landscapes. New mountains rose where land collided, new seas opened where it pulled apart, volcanic arcs traced the edges of closing oceans. Each of these features was a signpost, marking the progress of the larger pattern. The land itself bore the marks of these changes. Thick sequences of folded rock recorded past collisions. Broad plateaus hinted at ancient uplifts. Deep sedimentary basins told stories of long-gone seas. By reading these features, scientists can reconstruct not just where continents were, but how they moved, how fast they travelled, and what kinds of environments they passed through along the way. This reconstruction is not a single, finished picture. It is an ongoing effort, refined as new data and new methods become available. Satellites now measure the present-day motion of plates with millimetre-level precision. Laboratory experiments simulate the behaviour of rocks under extreme pressures and temperatures. Computer models explore how mantle convection might influence surface movements over geological time. Each of these tools adds another layer of detail to our understanding, helping to bridge the gap between the slow, hidden processes deep within the Earth and the visible features of the surface. Together they reveal a planet that is not static, but alive with motion at every scale. From the shifting of entire continents to the tiny vibrations of minerals aligning with a magnetic field. As this realization settles in, it can feel as though the world around you has gained a new dimension. The hills and valleys, the coastlines and plains are no longer just shapes on a map. They are snapshots in a long moving sequence, frames in a film that has been playing for billions of years and will continue long after we're gone. With that in mind, the formation of Pangea becomes less of an isolated event, and more of a natural outcome of the planet's constant restlessness. The continents did not come together because of a single dramatic cause. They gathered because the Earth never stops moving, because heat continues to rise from its depths, because plates continue to drift, collide, and separate. Long before anyone had a name for drifting continents, or a theory to explain how a world could pull itself together and then ease itself apart, the planet was already leaving behind quiet hints of its past. These hints were not written in ink or carved into monuments. They were pressed into layers of stone, locked inside crystals, and preserved in the delicate outlines of ancient life. For centuries, people walked across these records without realizing what they were stepping on. They saw mountains, cliffs, riverbanks, and quarries as useful or beautiful, but not as pages in a long and complicated story about a world that had once been arranged very differently. The earliest clues came from simple observation. Travellers, miners and scholars noticed that certain kinds of rocks and fossils appeared in places where they did not seem to belong. Seashells were found high in the mountains. The shapes of ancient plants appeared in stone far from any modern forest. Layers of sediment told stories of calm, shallow waters in regions that were now dry and inland. At first, these discoveries were often explained through local events, a great flood, a shifting river, or a dramatic change in climate. The idea that entire continents might have moved was far beyond what most people were willing to consider. As natural history grew into a more formal science, collections of fossils and rock samples began to fill museums and universities. Researchers started comparing findings from different parts of the world, and patterns slowly began to emerge. A plant fossil found in South America matched one discovered in Africa. A certain type of ancient reptile appeared in rock layers in both India and Antarctica. These were not small flying creatures that could have crossed oceans with ease. They were land animals and plants that depended on continuous stretches of ground to survive and spread. This raised a quiet but persistent question. How could the same species exist in places now separated by thousands of kilometres of open water? One possibility was that the oceans themselves were once smaller, and that land bridges had connected distant regions before sinking beneath the waves. For a time, this idea seemed reasonable, and it was used to explain many of the strange distributions of fossils and plants. However, as more evidence accumulated, the land bridge explanation began to feel strained. The proposed bridges would have needed to appear and disappear in very specific places and times, and there was little geological evidence to support their existence. The rocks beneath the oceans did not show signs of being former continents. Instead, they looked younger and different in composition, as if they had formed in a separate way altogether. The stones themselves offered another kind of clue. Geologists studying mountain ranges on different continents noticed that some of them shared remarkable similarities. The age of the rocks, their mineral content, and the way they were folded and layered seemed to match, even when those ranges were separated by wide oceans. It was as if a single, continuous belt of mountains had been cut apart and carried to different corners of the globe. One of the most striking examples comes from the Appalachian Mountains in North America and the Caledonian Mountains in Scotland and Scandinavia. When their rock layers are compared, they appear to be parts of the same ancient chain. The simplest explanation is that they were once connected, formed during the same period of collision between land masses that no longer sit side by side. Rocks also carry chemical signatures that can reveal the conditions under which they formed. Certain minerals crystallize only under specific temperatures and pressures. Finding those minerals in unexpected places can point to a past environment very different from the present one. For example, glacial deposits, layers of rock formed by the movement of ice, have been found in regions that are now warm and tropical. These deposits suggest that those areas were once located much closer to the poles, where large ice sheets could form and move across the land. Fossils provided some of the most compelling and relatable evidence. Unlike rocks, which can feel abstract and distant, fossils are the preserved remains of once living things. They invite a kind of connection across time. When scientists found identical fossils on separate continents, it was like finding the same family portrait in houses on opposite sides of the world. It hinted at a shared past that could not easily be explained by chance or coincidence. One well-known example is the fossil plant Glossopteris. This ancient seed fern lived during the late Paleozoic era and left behind distinctive leaf fossils. Those fossils have been found in South America, Africa, India, Australia, and Antarctica. Today, these places are separated by vast oceans and, in the case of Antarctica, extreme cold. The plant could not have crossed oceans, and it certainly could not have survived in the frozen environment that Antarctica has today. The simplest explanation is that all of these regions were once part of a single landmass, with a climate suitable for Glossopteris to thrive. Another example comes from the remains of a freshwater reptile called Mesosaurus. Fossils of this animal have been discovered in both South America and Southern Africa. Mesosaurus lived in lakes and rivers, not in the open ocean. It would not have been able to swim across a wide sea. Its presence on both continents suggests that those lands were once connected by freshwater environments that allowed the species to spread. As more of these connections were documented, the idea that the continents had once been joined began to gain a foothold. Still, the scientific community was cautious. The evidence pointed toward a shared past, but it did not yet provide a clear mechanism for how solid land could move across the surface of the planet. The stones offered more than just fossils and minerals. They also preserved the record of ancient climates. Certain types of sediment form only in specific conditions. For example, coal beds are created from the compressed remains of dense, swampy vegetation. Finding coal in places that are now cold and dry suggests that those regions once had warm, wet environments. Similarly, coral reefs, which require warm, shallow seas, have left behind limestone deposits in areas that are now far from any tropical ocean. By mapping the locations of these climate indicators, scientists could begin to reconstruct where different regions of the world must have been relative to the equator and the poles in the past. When they did this, a pattern emerged that made more sense if the continents had moved rather than if the climate zones themselves had shifted dramatically back and forth across a fixed map. There was also the matter of the shapes of the continents. This is perhaps the most visually striking clue, and one of the first to capture the public imagination. When you look at the coastlines of South America and Africa, the way they seem to fit together like two pieces of a puzzle is hard to ignore. While the match is not perfect, and erosion and rising sea levels have altered the edges over time, the overall alignment is suggestive. Geologists took this a step further by comparing not just the modern coastlines, but the edges of the continental shelves, the shallow underwater platforms that extend out from the land before dropping off into the deep ocean. When these outlines are matched, the fit becomes even closer. It is as if the true boundaries of the continents lie beneath the water, and the modern shorelines are just the worn and weathered edges of something that was once more neatly joined. Despite all of this, the idea of a united past world remained controversial. The main obstacle was the lack of a convincing explanation for how the continents could move. Rocks are heavy, the seafloor is solid. The idea that entire continents could slide across it seemed to many physically impossible. This is where the human side of the story becomes important. Science does not move forward in a straight line. It is shaped by personalities, by debates, by moments of insight and long periods of uncertainty. The clues written in stone and fossil were there, waiting to be read, but it took time for the right questions to be asked and the right tools to be developed. In the early 20th century, a German scientist named Alfred Wegener brought many of these pieces together. He was not a geologist by training, but a meteorologist and polar researcher. His interest in the shapes of the continents and the distribution of fossils led him to propose the idea of continental drift. He suggested that the continents were once joined in a single landmass and had since drifted apart. Wegener gathered evidence from many fields. He pointed to the matching coastlines, the shared fossils, the continuity of mountain ranges, and the climate indicators preserved in the rocks. He even proposed a name for the ancient supercontinent Pangea, meaning all lands. However, when he presented his ideas, they were met with skepticism and, in some cases, outright dismissal. Many geologists of the time felt that Wegener's evidence was interesting but not conclusive. More importantly, they argued that he had not provided a plausible mechanism for how continents could move. Wegener suggested that forces related to Earth's rotation and the pull of the moon might be responsible, but these explanations did not satisfy his critics. For several decades, the idea of continental drift lingered on the fringes of mainstream science. Some researchers continued to explore it, while others focused on different explanations for the same observations. The clues in stone and fossil remained, but their full meaning was still a matter of debate. Meanwhile, new discoveries were being made beneath the oceans. Advances in sonar and underwater exploration during and after the Second World War revealed the shape of the seafloor in unprecedented detail. Scientists found long, continuous ridges running through the middle of the world's oceans, as well as deep trenches near the edges of continents. When samples of oceanic rock were collected and analysed, they turned out to be much younger than most continental rocks. This suggested that the seafloor was being created and destroyed on a timescale far shorter than the continents themselves. It was as if the ocean floor was a conveyor belt, constantly renewing itself. Further studies revealed patterns in the magnetic properties of seafloor rocks. As molten rock cooled at the mid-ocean ridges, minerals within it aligned with the Earth's magnetic field. Because the planet's magnetic field has flipped direction many times over its history, these alignments formed a series of symmetrical stripes on either side of the ridges. This pattern made sense if new crust was being formed at the ridges and then pushed outward in both directions. These findings provided the missing mechanism. They showed that the seafloor itself was moving, carrying the continents along with it. The pieces of the puzzle that Wegener and others had assembled could now be placed into a broader framework known as plate tectonics. With this new understanding, the clues written in stone and fossil took on even greater significance. They were no longer just hints of a shared past. They were direct evidence of the movement of plates and the long history of continental assembly and breakup. The study of ancient rocks also revealed the scars of past collisions. In many places, geologists found belts of intensely deformed rock, where layers had been folded, faulted and metamorphosed under extreme pressure and heat. These belts often mark the sites where continents had once collided and fused together. By dating these rocks, scientists could determine when those collisions occurred and how they fit into the larger timeline of Earth's history. Fossils, too, began to tell a more detailed story. The appearance and disappearance of certain species in the rock record could be linked to changes in geography and climate caused by the movement of the continents. When landmasses joined, species that had evolved separately could suddenly interact, leading to competition, migration, and new evolutionary pathways. When landmasses separated, populations could become isolated, setting the stage for the development of new species. Even microscopic clues played a role. Pollen grains, spores, and tiny marine organisms left behind in sediments can be used to reconstruct past environments and climates. These microfossils can travel short distances by wind or water, but their overall distribution still reflects the arrangement of land and sea. By studying them, scientists can fill in details about ancient coastlines, ocean currents, and temperature patterns. As all of these lines of evidence came together, the picture of a once united world grew clearer. The stones and fossils were not just isolated curiosities, they were parts of a global record, a long interconnected archive of the planet's surface history. This realization changed the way scientists approach geology and paleontology. Instead of studying regions in isolation, they began to think in terms of entire systems that spanned the globe. A mountain range in one continent could be linked to a plateau in another. A fossil bed in one country could be part of a much larger pattern that crossed oceans and hemispheres. For the wider public, these ideas also reshaped how people thought about the Earth. The notion that the continents had once been joined invited a different sense of connection between distant places. The ground beneath your feet and the land on the far side of the world were no longer completely separate. They were parts of a shared history, carried to their current positions by a slow and patient planet. There is something quietly powerful about that idea. It suggests that the world is not a collection of isolated pieces, but a single dynamic system, constantly rearranging itself. The clues written in stone and fossil are reminders of that unity, preserved in forms that can last for hundreds of millions of years. As researchers continue to explore new regions and develop new techniques, they keep finding more details to add to this story. High-precision dating methods allow scientists to pin down the timing of events with greater accuracy. Computer models can simulate past continental arrangements and test how well they match the geological and fossil evidence. Even satellite data, which tracks the current movement of plates, helps refine our understanding of how these processes have worked in the past. Yet for all of this sophistication, the foundation of the story remains surprisingly simple. It begins with noticing what is there: a shell in a mountain, a leaf in stone, a line of similar rocks on different continents. It grows through careful comparison and the willingness to ask questions that challenge familiar assumptions. The first clues were not grand revelations. They were small, often overlooked details that only gain significance when placed in a broader context. A fossil here, a rock layer there, a coastline that seems to match another across the sea. Over time, these pieces formed a pattern that pointed toward a world that had once been whole. If you spread a world map out on a table and let your eyes wander without any particular goal, there is a moment that often arrives on its own. It is the quiet realization that some of the shapes seem to recognize each other. The eastern edge of South America curves in a way that feels strangely familiar, as if it is waiting for something. The western coast of Africa carries a matching line, not perfect, not exact, but close enough to spark a sense that these two distant places might once have been neighbours. It is a simple observation, almost playful, the kind of thing you might notice absent-mindedly while tracing coastlines with a finger. Yet behind that gentle curiosity sits one of the most powerful visual clues in the story of how the world was once arranged. For a long time, this apparent fit was treated as a coincidence. After all, coastlines are shaped by waves, rivers, rising and falling seas, and the slow crumbling of rock. They change over time, sometimes dramatically. Expecting them to line up neatly across an ocean seems like asking too much. Still, the idea lingered, because the resemblance was not limited to just one pair of continents. Other edges also seemed to echo each other in subtle ways, hinting at a broader pattern rather than a single lucky match. Early map makers noticed these similarities, even if they did not always attach deep meaning to them. As global exploration expanded and more accurate maps became available, the shapes of the continents grew clearer. The better the maps became, the harder it was to ignore the way certain coastlines appeared to complement one another. This was not yet proof of anything, but it was a visual invitation to think differently about the surface of the planet. When scientists began to take this observation seriously, they did something simple but revealing. Instead of comparing the modern shorelines, which are shaped by tides and erosion, they looked at the edges of the continental shelves. These shelves are the shallow submerged platforms that extend out from the land before dropping into the deeper parts of the ocean. They represent the true geological boundary of the continents, rather than the ever-changing line where land meets water. When these underwater outlines were traced and compared, the fit between certain continents became even more striking. South America and Africa in particular seemed to lock together more convincingly along these deeper edges. It was as if the modern coastlines were just the worn, uneven rims of a much older, cleaner break. This approach transformed a casual visual similarity into something that could be measured and tested. Researchers began using mathematical techniques to see how well different continental margins could be aligned. They adjusted for the effects of erosion and sediment buildup, trying to reconstruct what the original edges might have looked like when the continents were still joined. The results were compelling. The match was not perfect, but it was far better than chance alone would suggest. And once attention was drawn to this method, other alignments began to emerge. Parts of North America appeared to correspond with sections of Europe and Greenland. Australia showed connections to Antarctica. India, now far to the north, seemed to have once been tucked against the southern landmasses. These matching edges were like the outlines of a puzzle that had been taken apart and scattered across a table. Each piece had been worn down and reshaped slightly, but the original connections were still there, waiting to be recognised. Yet maps alone were not enough to convince everyone. A skeptic could argue that with enough creativity, almost any shapes could be made to fit. The real strength of this clue came from how well it lined up with the other evidence from rocks, fossils, and ancient climates. The matching coastlines were not isolated coincidences. They were part of a larger, consistent picture. Consider what happens when two continents are placed together based on their shelf edges. Rock formations that were once separate suddenly line up. Fossil sites that seemed strangely distributed now fall into more sensible patterns. Glacial deposits that once appeared scattered across warm regions form continuous belts, suggesting a single, coherent, ice-covered area in the past. This layering of evidence turned a visual curiosity into a powerful argument. The maps did not just look like they should match. When they were matched, they helped explain a wide range of geological and biological observations that had previously been difficult to connect. The process of refining these matches became more sophisticated over time. Early attempts relied on printed maps and careful hand-drawn outlines. Scientists would cut out shapes of continents and physically move them around on a table, searching for the best fit. It was a hands-on, almost playful method, but it laid the groundwork for more precise approaches. Later, computers took over much of this work. Digital models allowed researchers to simulate the movement of plates backward through time, guided by data from rock ages, magnetic patterns, and known plate boundaries. These models could test different configurations, showing which arrangements best matched the available evidence. Through this work, a clearer image of the ancient world began to take shape. Pangea was not a simple, smooth-edged landmass. Its outline was complex, with deep inlets, long peninsulas, and broad interior regions far from any ocean. The continents that now seem so separate were once parts of this larger whole, connected in ways that made sense not just visually, but geologically and biologically. There is something quietly satisfying about this kind of matching. It appeals to a very human instinct, the desire to find patterns and connections. When two pieces fit together, it feels like a small victory, a moment of understanding. In the case of the continents, that feeling is magnified by the scale of what is being connected. These are not puzzle pieces you can hold in your hands. They're entire regions of the planet, reunited in the mind through careful observation and analysis. The history of how this idea was received also reflects the cautious nature of science. Even when the maps seemed to line up, many researchers were reluctant to accept the implications. The visual fit suggested a past connection, but it did not yet explain how that connection could have been broken. Without a clear mechanism for movement, the matching shapes were seen by some as an interesting coincidence rather than a definitive clue. This skepticism played an important role. It pushed proponents of the idea to look for stronger, more quantitative evidence. They did not just rely on what looked right. They measured angles, distances, and curvatures. They compared rock types and fossil distributions across the proposed joins. They tested whether the matches held up when different datasets were brought into the picture. Over time, this process strengthened the case. The maps became one line of evidence among many, each one reinforcing the others. Together they painted a picture of a world that had once been assembled differently and that had changed through processes that were only beginning to be understood. One of the more subtle aspects of this work involves the concept of plate rotation. Continents do not just slide in straight lines. They can also rotate as they move, pivoting around points called Euler poles. This means that when you try to match two continental edges, you cannot simply push them together like flat pieces on a table. You have to account for how they might have turned relative to each other over time. Modern reconstructions take this into account, using mathematical models to rotate and shift plates in 3 dimensions. This adds another layer of complexity, but it also allows for much more accurate fits. When this is done, the ancient alignments often become clearer, reinforcing the idea that the continents were once parts of a single, connected system. These reconstructions also help explain why some matches are not obvious at first glance. Erosion, sedimentation, and changes in sea level can obscure the original edges of continents. River deltas can push coastlines outward. Ice sheets can carve away large sections of land. Over millions of years, these processes can significantly alter the shape of a continent's margin. By looking beneath these surface changes and focusing on the deeper structure of the continental crust, scientists can see past the modern shoreline to the more stable framework underneath. This is where the true outlines of the ancient connections are preserved. The story of matching maps is not just about South America and Africa. It extends around the globe. The eastern coast of North America shows connections to parts of Europe and Northwest Africa. The southern edges of Australia align with sections of Antarctica. India, now welded to Asia, can be traced back to a position alongside Africa and Antarctica before it began its long journey northward. Each of these matches adds another piece to the larger picture. Together they form a network of connections that make sense only if the continents were once assembled in a very different way. There is also an interesting feedback loop between these visual matches and the study of plate tectonics. As scientists learned more about how plates move, they could refine their reconstructions of past configurations. In turn, those reconstructions could be tested against the geological and fossil evidence. When everything lined up, it provided a strong confirmation that the underlying model was on the right track. This interplay between observation and theory is a hallmark of scientific progress. The maps did not stand alone. They invited questions which led to new investigations, which in turn led to better explanations. The process was not always smooth or straightforward, but it gradually built a more complete understanding of the planet's history. There is also a cultural side to this story. The idea that the continents were once joined captured the public imagination in a way that many scientific theories do not. It is easy to picture. It feels almost like a storybook image, a world where all the lands touch, where animals could roam freely across what are now vast oceans. This accessibility helped the idea spread beyond academic circles. It appeared in textbooks, documentaries, and popular science writing. Over time, it became part of the way people thought about the Earth, a reminder that the world we see today is not fixed, but part of a much longer, ongoing narrative. At the same time, this popularity also brought challenges. Simplified images of Pangea sometimes gave the impression that the supercontinent was a neat, almost symmetrical shape, like a single, rounded island. In reality, its outline was complex and irregular, shaped by the specific histories of the plates that formed it. Understanding this complexity requires looking beyond the most obvious matches and considering the full range of geological evidence. The maps, then, are both an entry point and a guide. They draw attention to the idea of a connected past, but they also point toward the deeper processes that made that connection possible. They encourage a way of seeing the world that looks for relationships rather than isolated features. If you think about it, this approach can be applied at many scales. A single rock layer can be part of a mountain range. A mountain range can be part of a continent. A continent can be part of a supercontinent. Each level of connection adds context and meaning to the one below it. In the case of Pangea, the matching maps help bridge the gap between the abstract idea of plate tectonics and the tangible reality of the world's surface. They show, in a way that can be grasped at a glance, that the continents are not random shapes scattered across the globe. They are pieces of a larger whole, shaped by a shared history of movement and change. As new data continues to emerge, these matches are refined and sometimes adjusted. Improved measurements of the seafloor, better dating of rock formations, and more detailed models of plate motion all contribute to a clearer picture of how the continents were arranged at different points in the past. This ongoing refinement is another reminder that scientific understanding is not static. The broad outline of the idea that the continents were once joined is now widely accepted, but the details, the exact positions, the timing of different collisions and separations are still being worked out. In a way, this mirrors the process that first led people to notice the matching maps. It begins with a simple observation, a sense that something fits. It grows through careful measurement and comparison, and it evolves as new tools and new perspectives become available. The story of maps that should not match, but do, is therefore about more than just the shape of coastlines. It is about how humans learn to read the surface of the planet, how they move from curiosity to evidence, from suggestion to explanation. It shows how a visual pattern can open the door to a deeper understanding of processes that operate on scales far beyond everyday experience. Beneath the floor you're standing or sitting on right now, beneath the layers of wood, concrete, soil and stone, there is a world that feels nothing like the calm surface we experience every day. It is not a place of sudden motion or sharp boundaries. Instead, it is a realm defined by pressure, heat, and a kind of slow, persistent movement that never truly stops. This hidden world is where much of the story of Pangea and of Earth itself quietly unfolds. To reach it in your imagination, you have to travel downward, past the familiar crust of the planet, and into the vast interior that makes up most of Earth's volume. The crust, which feels so solid and permanent to us, is actually a thin skin compared to what lies below. On average, it is only a few tens of kilometers thick, a fragile shell floating atop a much deeper and more complex structure. Directly beneath the crust lies the upper mantle, a region made of rock that is solid, but not rigid in the way we usually think of stone. The temperatures here are high enough that the minerals inside can slowly deform, bending and flowing over long periods of time. This ability to move, even at a pace measured in centimetres per year, is what allows the surface of the planet to change so dramatically over millions of years. The mantle extends deep into the Earth, reaching down nearly 3,000 kilometres toward the core. It is not uniform. Different layers have different compositions, temperatures and physical properties. Some parts are slightly softer and more prone to flow, while others are stiffer and more resistant. Together, these layers form a complex system that transfers heat from the interior of the planet toward the surface. This heat comes from two main sources. One is the leftover energy from Earth's formation, when countless collisions and compressions turned a cloud of cosmic material into a dense, spinning planet. The other comes from the slow decay of radioactive elements within the mantle and core. These elements release energy as they break down, providing a steady, long-lasting source of warmth that keeps the interior from cooling too quickly. As heat moves upward through the mantle, it sets the stage for motion. Hotter, less dense material tends to rise, while cooler, denser material sinks. This creates broad convection currents, slow-moving loops of rock that can take tens or hundreds of millions of years to complete a single cycle. These currents are not smooth or uniform. They twist, split, and interact in complex ways, influenced by the shape of the core, the composition of the mantle, and the movement of the plates above. It is these deep, slow currents that help drive the motion of tectonic plates at the surface. The plates themselves are made up of the crust and the uppermost part of the mantle, forming a rigid layer known as the lithosphere. This layer is broken into separate pieces that rest on a softer, more flexible region of the mantle called the asthenosphere. The asthenosphere's ability to flow even slightly allows the plates above it to move. This movement is not like a boat gliding over water. It is more like a heavy object resting on a very thick, slowly shifting cushion. The plates are pushed and pulled by a combination of forces, some coming from the rising of hot material beneath mid-ocean ridges, and others from the sinking of cold, dense plates at subduction zones. At mid-ocean ridges, where plates move apart, molten rock from the mantle rises to fill the gap. As it cools and solidifies, it becomes part of the plate, creating new sea floor. This process, known as seafloor spreading, acts like a slow conveyor belt, carrying the plates away from the ridge on either side. The newly formed crust is hot and buoyant, sitting higher than older crust farther away from the ridge. As this crust travels outward, it cools, becomes denser, and sinks lower into the mantle. Eventually it may reach a region where it encounters another plate. If that other plate is less dense, the oceanic crust will bend downward and slide beneath it, sinking back into the mantle. This is the process of subduction, and it is one of the main ways the Earth recycles its surface material. These two processes, creation at ridges and destruction at subduction zones, form a continuous cycle. New crust is born, travels across the surface of the planet, and then returns to the depths. The continents ride along on this moving system, carried by the plates that support them. The power involved in this cycle is immense, but it is expressed in a way that feels almost gentle at the human scale. A plate might move only a few centimetres in a year. Over a lifetime, that adds up to a distance you could cover in a few steps. Over 10 million years, it can mean a journey of hundreds of kilometres. During the long path toward the formation of Pangea, this slow movement was relentless. Plates carrying ancient landmasses drifted toward one another, guided by the balance of forces acting on them. The closing of an ocean basin could take tens of millions of years, as the seafloor between two continents was gradually consumed as a subduction zone. As the gap narrowed, the environment along the margins changed. Coastal regions became more active, with volcanic arcs forming where one plate sank beneath another. Earthquakes mark the points where the plates locked and then slipped, releasing built-up stress. Over time, the approaching continents began to influence each other's climates, ecosystems, and geological development. When two continents finally met, the energy involved did not disappear. Instead of sinking, their thick, buoyant crusts pressed against each other. The result was a slow, grinding collision that folded and thickened the crust, pushing up mountain ranges that could stretch across entire regions. These mountains were not formed in a single dramatic event, but through countless small movements, each one adding a little more height, a little more complexity to the landscape. Deep beneath these rising ranges, the roots of the mountains extended far into the mantle. The added weight of this thickened crust caused the underlying mantle to flow outward, much like a soft surface bulges when something heavy is placed on it. This process, known as isostasy, helped balance the mass of the mountains and influenced how the surrounding regions rose or sank in response. The slow power beneath your feet also shaped the chemistry of the planet. As plates moved and rocks were pushed deep into the mantle or brought back to the surface, elements were redistributed. Carbon, for example, was locked into rocks at the surface, carried down into the mantle at subduction zones, and later released back into the atmosphere through volcanic eruptions. This long-term carbon cycle played a role in regulating Earth's climate over geological timescales. Water, too, was part of this deep exchange. Oceanic crust carried water trapped in its minerals down into the mantle. Some of this water was released at depth, helping to melt rock and fuel volcanism. Over time, this process helped maintain the balance between the water in the oceans and the water stored within the Earth itself. These hidden exchanges remind us that the surface and the interior of the planet are not separate systems. They are deeply connected, linked by the slow movement of plates and the flow of material between different layers. During the era when Pangea was coming together, these connections became especially important. The convergence of large land masses altered the patterns of mantle flow beneath them. As continents collided and thickened, they acted like insulating blankets, trapping heat below. This could influence where hot material rose and where new rifts might form in the future. In some cases, the buildup of heat beneath a large, stable landmass could weaken the crust from below. Over time, this weakening might lead to the formation of a rift, a long, narrow zone where the land begins to pull apart. If the rifting continues, it can eventually lead to the birth of a new ocean basin, reversing the process that once brought the continents together. This means that the same slow power that assembled Pangea also carried within it the seeds of its eventual breakup. The planet's interior does not favour one arrangement forever. It responds to changes at the surface and adjusts its flow accordingly, setting the stage for the next phase of the supercontinent cycle. From the perspective of the deep Earth, the surface is a kind of shifting pattern of weights and shapes. Large continents change how heat escapes from the mantle. Mountain ranges alter the distribution of mass. Ocean basins open pathways for new crust to form and old crust to sink. All of these factors feed back into the system, influencing the direction and strength of mantle currents. This feedback loop makes the planet's behaviour both complex and remarkably self-organising. There is no single control centre directing the movement of plates or the flow of heat. Instead, the system evolves through the interaction of many parts, each responding to the others in ways that can lead to long-term patterns like the assembly and breakup of supercontinents. Understanding this system has been one of the great challenges of Earth science. Much of the mantle is inaccessible, hidden beneath thousands of kilometres of rock. Scientists rely on indirect methods to study it. Seismic waves from earthquakes provide one of the most important tools. As these waves travel through the Earth, they change speed and direction depending on the properties of the material they pass through. By analysing these changes, researchers can create images of the mantle structure, revealing regions that are hotter, cooler, denser, or less dense. These images have shown that the mantle is far from uniform. There are large, slow-moving features, sometimes called mantle plumes, that appear to rise from deep within the Earth. These plumes can create hotspots at the surface, leading to chains of volcanoes as a plate moves over them. The Hawaiian Islands are a well-known example of this process in action. Other regions of the mantle appear to be cooler and denser, associated with the remnants of subducted plates that have sunk deep into the interior. These sunken slabs can influence mantle flow, redirecting currents and affecting where heat rises. During the time leading up to Pangea, these deep structures likely played a role in guiding the movement of plates. The locations of major subduction zones and the presence of large mantle features could have influenced which directions the continents drifted and where they eventually came together. The idea that the deep Earth can shape the surface, and that the surface can in turn shape the deep Earth, adds another layer to the story of a moving planet. It is not just a matter of plates sliding around on a passive foundation. It is a dynamic system, with interactions that span the entire depth of the planet. This perspective also highlights the patience of geological processes. The mantle does not rush. Changes that matter at the surface take millions of years to develop. A rising plume might take tens of millions of years to reach the crust. A sinking plate can continue its descent for just as long. For humans, this scale of time is difficult to grasp. Our lives are measured in decades. Our recorded history spans a few thousand years. The processes that shape continents operate on a timeline that makes even the longest human stories feel brief. Yet the effects of these processes are all around us. The mountains you see on the horizon, the shape of the coastline, the distribution of earthquakes and volcanoes, all are expressions of the slow power beneath your feet. They are surface ripples on a deep, ongoing flow of energy and material. When you consider the formation of Pangea in this light, it becomes clear that it was not a special or isolated event. It was one outcome of a system that has been running since the planet's early days. The same forces that brought the continents together will, given enough time, pull them apart again and guide them into new arrangements. This understanding can change the way you think about stability and change. The world feels solid, dependable, and fixed, but in reality it is part of a long, slow transformation. The ground beneath you is not a permanent stage. It is a moving platform carried by deep currents that will continue their work long after any trace of our own presence has faded. There is something quietly humbling about that thought. It places human time within a much larger frame, one where even the rise and fall of entire continents is just part of an ongoing cycle. As the continents continued their gradual approach toward one another in the lead up to Pangea, the deep processes of the mantle and the surface movements of the plates remained tightly linked. Each collision, each closing ocean, each rising mountain range was both a result of what was happening below and a new influence on how the system would evolve. This layered, interconnected story is what gives the planet its sense of continuity. The past is not sealed off from the present. The forces that shaped ancient worlds are still at work today, guiding the slow rearrangement of the surface and setting the stage for what will come next. From the surface, continents seem like the most reliable features of the planet. They hold cities, forests, deserts, and coastlines in place. They give shape to maps and names to places. They feel as solid and immovable as anything in the natural world. Yet when you widen your sense of time, when you step back far enough to see beyond centuries and even beyond the span of recorded history, those vast stretches of land begin to look less like fixed foundations and more like slow, wandering forms, drifting across the face of the earth with a patience that makes their movement easy to overlook. It can help to imagine the continents not as rigid slabs, but as enormous, heavy travellers. They do not stride or rush. They do not change direction on a whim. They move in a way that is closer to sleepwalking, guided by deep forces they cannot see and cannot resist. Their journeys are measured in centimetres per year, but their destinations lie thousands of kilometres away. Each continent rests on a tectonic plate, and it is the plate that truly moves. The land you recognise, the hills and valleys, the rivers and plains, are all passengers on a larger structure of crust and upper mantle. Some plates carry a single major continent. Others support a mix of continental and oceanic crust. A few are almost entirely oceanic, holding no land above the waves at all. This arrangement means that continents do not always travel alone. A plate might carry a continent on one side and a wide stretch of seafloor on the other. As the plate moves, both are carried together, maintaining their relative positions even as they cross the globe. Over long periods, this can bring continents close to one another or pull them apart depending on the directions the plates take. The idea of drifting land can feel counterintuitive because we're used to thinking of movement in terms of things we can watch. A car crosses a road, a cloud passes overhead, a shadow slides across the ground. The motion of continents is so slow that it escapes this kind of direct perception. You could live your entire life on the same piece of land and never notice that it has travelled a few meters in a particular direction. Yet there are ways to make this movement tangible. Modern technology allows scientists to measure the positions of points on the Earth's surface with extraordinary precision. Using satellites and ground-based receivers, they can track how those points shift over time. In many places, the movement is just a few millimeters or centimeters each year, but it is consistent and measurable. The ground is not standing still. It is drifting steadily and quietly. When you extend this rate of movement across millions of years, the scale of the journey becomes easier to appreciate. At a speed of just 2 centimeters per year, a continent can travel 200 kilometers in 10 million years. Over 100 million years, that distance becomes 2,000 kilometers, roughly the width of a large ocean basin or the length of an entire country. These are the kinds of distances involved in the story of Pangea. The continents that now sit far apart were once neighbours because they were carried there by their plates, step by slow step across the surface of the planet. The paths they took were not straight lines. Plates can change direction over time, influenced by shifts in the balance of forces acting on them. The push from new crust forming at a ridge, the pull of a sinking slab at a subduction zone, and the drag of the underlying mantle can all vary. As these influences change, the plate's course can curve, rotate, or even reverse. This is why the history of continental movement often looks like a series of loops and arcs rather than simple, direct paths. A landmass might drift northward for tens of millions of years, then begin to swing east or west. It might rotate slightly as it travels, changing how it is oriented relative to its neighbours. These rotations can have important consequences. When two continents approach each other, the angle at which they meet can shape the kind of mountains that form and the way their crusts are deformed. A head-on collision might create a wide, thick mountain belt. A more oblique approach might lead to long sliding boundaries where the land masses scrape past each other before finally locking together. During the long approach to Pangea, several major continental blocks were on converging paths. What is now North America, parts of Europe, Africa, South America, Antarctica, Australia, and India were all moving within a global system that favoured gathering rather than spreading. Each one followed its own route, guided by the plates beneath it and the deep currents of the mantle below. Some of these land masses travelled great distances. India, for example, began its journey as part of a southern grouping of continents. Over time, it broke away and moved steadily northward, crossing an ancient ocean before colliding with Asia. That collision, which happened after Pangea had already formed and begun to break apart, created the Himalayas and continues to shape the region today. Other continents had more complex journeys, involving multiple collisions and separations. Pieces of what is now Europe, for instance, were once scattered across different plates. They drifted, collided, and fused over time, creating a patchwork of crustal blocks that now form a single landmass. This kind of history is recorded in the rocks, which show signs of having been formed in very different environments and later brought together. One way to trace these movements is through paleomagnetism, the study of ancient magnetic fields preserved in rocks. As mentioned before, when molten rock cools, it locks in a record of the Earth's magnetic field at that time. Because the magnetic field is roughly aligned with the planet's rotation axis, these records can tell scientists the latitude at which the rock formed. By collecting and analysing samples from different regions and different ages, researchers can reconstruct the past positions of continents. They can see how far north or south a landmass was at a given time, and how that position changed over millions of years. This provides a kind of map of continental journeys, showing paths that span half the globe. These reconstructions often reveal surprising stories. A region that is now temperate might once have been near the equator, experiencing tropical conditions. A land that now lies in the southern hemisphere might have spent a long period in the north. These shifts help explain the presence of certain fossils and rock types in places where they seem out of place today. The idea of continents as travellers also helps make sense of ancient climates. Climate is strongly influenced by latitude. Regions near the equator tend to be warmer, while those closer to the poles are cooler. As a continent drifts, it carries its ecosystems through these climate zones. Over time, this can lead to major changes in vegetation, animal life, and the types of sediments that are deposited. For example, a landmass that moves from the tropics toward higher latitudes might see lush forests give way to more seasonal environments and eventually to glacial conditions. The rocks formed during each phase preserve a record of those changes, creating a layered history that can be read millions of years later. During the assembly of Pangea, some continents moved into positions that placed large parts of the supercontinent near the equator. This had significant effects on global climate. With so much land in low latitudes, there was a large area exposed to intense sunlight. This influenced patterns of weathering, erosion, and the formation of soils. It also affected the distribution of rainfall, with some interior regions becoming dry and others experiencing seasonal monsoons. The interior of a large landmass can behave very differently from a coastal region. Far from the moderating influence of the ocean, temperatures can swing more dramatically between day and night and between seasons. Rainfall can be less reliable, leading to the development of arid or semi-arid environments. These conditions shape the kinds of plants and animals that can survive there and leave distinctive marks in the geological record. As the continents drifted into these configurations, they did not just change their own environments, they also influenced the oceans around them. The opening and closing of seaways altered ocean currents, which in turn affected how heat was distributed around the planet. These changes could amplify or moderate climate shifts, creating feedback loops that link the movement of land to the behaviour of air and water. This interconnectedness means that the journey of a continent is never just its own story. It is part of a larger system that includes the atmosphere, the oceans, and the deep interior of the Earth. Each movement sends ripples through this system, changing conditions far beyond the immediate area. The drifting of continents also plays a role in the long-term cycling of elements like carbon. As land moves into different climates, the rates of weathering and erosion change. In warm, wet regions, chemical weathering can break down rocks more quickly, pulling carbon dioxide out of the atmosphere and locking it into minerals. In colder or drier regions, this process slows. Over millions of years, these shifts can influence global climate by altering the balance of greenhouse gases. This means that the slow, silent travel of continents can have effects that reach all the way into the sky. The shape of the land and its position on the globe can help determine how warm or cool the planet becomes over geological timescales. There is also a biological dimension to this movement. When continents drift apart, they can isolate populations of plants and animals. Over time, these isolated groups can evolve in different directions, leading to the development of new species. When continents come together, previously separate ecosystems can merge, allowing species to interact, compete, and sometimes spread into new territories. The formation of Pangea created vast connected land areas where animals and plants could move across regions that are now separated by oceans. This connectivity had a profound impact on the distribution of life. It allowed certain species to spread widely, while others became confined to particular environments within the supercontinent. Fossil records from this time show patterns that make sense only if the land was connected. The presence of similar species across what are now different continents reflects the freedom of movement that existed when those lands were joined. The idea of continents as sleeping giants also speaks to the way their movement is often revealed through sudden, dramatic events. Most of the time, the drift is quiet and unremarkable. Then, occasionally, the built-up stress along a plate boundary is released in an earthquake, or magma finds a path to the surface in a volcanic eruption. These moments are brief flashes of activity that hint at the deeper ongoing motion beneath. Mountain ranges too are reminders of this long process. Their heightened form reflect millions of years of collision and uplift, followed by millions more of erosion. They are not just static features. They are records of past movement, frozen in place for a time before being worn down, and in some cases reshaped by future events. The continents themselves carry scars of their journeys, fault lines, folded rock layers, and belts of metamorphic rock mark, places where plates have collided or slid past each other. These features can often be traced across wide regions, revealing the paths of ancient boundaries that no longer exist at the surface. As scientists piece together these records, they can reconstruct not just where continents were, but how they interacted. They can see when a landmass was part of a larger group, when it broke away, and when it joined another. These reconstructions form the backbone of our understanding of how Pangea came together and how it later broke apart. It is also worth considering how this perspective changes the way we think about maps. A modern map shows the world as it is now, a snapshot in a long film. The boundaries and shapes feel definitive, but they are only temporary. Given enough time, those shapes will change. New oceans will open, old ones will close, continents will gather in new configurations that no human has ever seen. In this sense, every place on Earth is part of a journey that is still ongoing. The land beneath you has a past that stretches back through multiple supercontinents, and a future that will carry it into arrangements that are hard to imagine. The drift that once brought the pieces of Pangea together will, in the long run, lead to new separations and new unions. There is something quietly poetic about this, even when described in the straightforward language of geology. The planet is not a finished object. It is a process. The continents are not fixed actors. They are participants in a slow global movement that has been unfolding for billions of years. This way of seeing the world can make even the most familiar landscape feel a little different. A hillside becomes a fragment of a long-travelled plate. A coastline becomes a temporary edge in a much larger story. A mountain range becomes a monument to a collision that happened in a world that no longer exists in the same form. As the slow drift continues, it leaves behind clues that scientists use to refine their reconstructions. Each new study, each new set of measurements, adds another detail to the map of the past. The paths of the sleeping giants become clearer, their encounters more precisely timed, their journeys more fully understood. And yet, there is always more to learn. The deeper we look, the more complex the story becomes. Plates do not move in isolation. They influence each other. They respond to changes in the mantle. They carry with them the memory of past collisions and separations, which shape how they behave in the future. This layered history is what makes the study of continental drift so rich. It is not just about where the land was at a certain time. It is about how the entire planet works as a connected system, where deep processes and surface features are linked across vast spans of time. As the continents continued their slow approach during the era that would eventually give rise to Pangea, their movements were guided by this deep, persistent power. They drifted, rotated, collided, and fused, each step adding to the growing landmass that would, for a time, dominate the face of the Earth. Between the slow drift of continents and the grand idea of a united world, there lies a landscape of change that often goes unnoticed, because it unfolds on a timescale that does not match the rhythm of daily life. Oceans open where there was once solid ground. Mountains rise where seas once rolled in gentle waves, and in between these moments of creation and collision, there are long stretches of quiet transformation, where the planet seems almost still, even as it continues its patient work. To begin with the oceans, it helps to imagine the surface of the Earth as something that can stretch and thin, rather than as a single, unbroken shell. When forces within the mantle begin to pull a plate apart, the crust above can start to crack. At first, these cracks might appear as a series of shallow valleys, known as rifts, where the land sinks slightly as it is pulled in two directions. These regions can be marked by volcanic activity, as magma rises through the thinning crust and spills onto the surface. Over time, if the pulling continues, the crust can become so thin that it breaks completely. When this happens, a new boundary is formed, and molten rock from the mantle can rise directly into the gap. As it cools, it creates new oceanic crust. Water from the surrounding regions begins to fill the low-lying area, and a narrow sea is born. Given enough time, that narrow sea can widen into a full ocean basin. This is not just a theoretical process. It is happening today in places like the East African Rift, where parts of the continent are slowly pulling apart. Lakes fill the rift valleys, volcanoes dot the landscape, and the ground itself is gradually lowering. If this process continues for millions of years, a new ocean could form, splitting Eastern Africa from the rest of the continent. In the deep past, similar processes played out on a much larger scale. Ancient oceans opened as land masses pulled apart, creating new seafloor and new pathways for water and life to move around the globe. These oceans were not permanent features. They were part of a cycle, born from separation, and destined, in many cases, to be closed again by collision. The opening of an ocean can feel like an act of creation, but it also sets the stage for its eventual end. As new crust forms at a mid-ocean ridge and moves outward, it eventually reaches the edges of continents or other plates. There, it can begin to sink back into the mantle at subduction zones. Over millions of years, this process can consume an entire ocean basin, drawing the continents on either side closer together. This slow narrowing of an ocean is a quiet but powerful phase in the life of the planet. The seafloor disappears piece by piece, carried downward into the mantle. Volcanic arcs often form along the margins, tracing the line where one plate slides beneath another. These arcs can be chains of islands or coastal mountain ranges, depending on the nature of the plates involved. As the gap between continents shrinks, the environments along their edges change. Shallow seas can become narrower and more enclosed. Currents can be redirected or weakened. The chemistry of the water can shift, affecting marine life. Sediments that once spread across broad continental shelves may begin to pile up in more confined basins. Eventually the two land masses meet. When they do, the ocean between them is gone, replaced by a zone of intense geological activity. The crust thickens as layers of rock are pushed on top of each other. The pressure and heat transform existing rocks into new forms, creating bands of metamorphic stone that record the violence of the collision. This is where mountains are born. The rise of a mountain range is not a sudden event. There is no single moment when flat land becomes a towering peak. Instead, it is a gradual process, driven by the slow but relentless movement of plates. As continents press together, the crust has nowhere to go but up and down. It thickens and bulges, pushing some material deep into the mantle and forcing other parts upward toward the sky. The mountains that result can stretch across entire continents. They can form long, continuous chains or broad, high plateaus. Over time, they influence everything around them, from weather patterns to river systems to the distribution of plants and animals. Air flowing toward a mountain range is forced to rise. As it rises, it cools, and the moisture it carries can fall as rain or snow on one side of the range. The other side, in the shadow of the peaks, can become much drier. This effect, known as a rain shadow, can create stark contrasts in climate over relatively short distances. rivers respond to these changes as well. New slopes give water new paths to follow. Streams carve valleys into rising terrain, carrying sediment away from the peaks and depositing it in lowlands and coastal regions. Over time, these sediments can form thick layers of rock, preserving a record of erosion that can be read millions of years later. As mountains rise, they are also being worn down. Wind, rain, ice, and gravity all work to break rock into smaller pieces and move it downhill. This erosion is not a sign of weakness or failure. It is part of the same cycle that created the mountains in the first place. The material removed from the peaks becomes the raw material for new landscapes elsewhere. This balance between uplift and erosion can persist for a long time. In some cases, the rate of uplift is roughly matched by the rate of erosion, allowing a mountain range to maintain its height for millions of years. In others, erosion eventually wins, and the range is worn down into rolling hills or even flat plains. Between the opening of oceans and the rising of mountains, there are long periods of relative calm. These are the times when the major plate boundaries are far away, and the land sits in the interior of a large, stable region. The crust is thick and strong. There is little volcanic activity. Earthquakes are rare. From the surface, the world can feel settled and unchanging. These quiet intervals are the silence in between, not a true absence of motion, but a phase where the most dramatic changes are happening far away. The land in these regions still moves, still rises and falls slightly as the mantle shifts beneath it, but the changes are subtle. Over millions of years, however, even this gentle motion can shape the landscape. In the interior of a large landmass, rivers can wander across broad, flat plains, depositing layers of sediment that build up over time. These layers can become thick sequences of sandstone, shale, and limestone, recording the history of ancient rivers, lakes, and shallow seas. Fossils preserved in these rocks provide snapshots of the life that once thrived in these stable environments. These interior regions can also be influenced by changes at the edges of the continent. The rise of mountains along a distant boundary can alter the flow of air and water across the entire landmass. The opening or closing of a seaway can change global climate patterns, affecting rainfall and temperature far from the coast. During the long path toward the formation of Pangea, the world experienced all of these phases. Ancient oceans opened as land masses pulled apart. Others closed as plates converged. Mountain ranges rose where continents collided, while vast interior regions enjoyed long periods of relative stability. The supercontinent itself was not formed in a single, neat sequence. Different parts of it came together at different times. In some regions, collisions happened early, creating mountain belts that would later be buried or eroded as new landmasses joined. In others, oceans persisted for longer, keeping parts of the world separate until later in the process. One of the ways scientists trace this complex history is by studying the ages of rocks in different mountain ranges. By dating when the rocks were formed or transformed, they can identify periods of collision and uplift. When similar ages and rock types appear in different parts of the world, it can suggest that those regions were once part of the same event, a single, continuous mountain-building episode that spanned what are now separate continents. Another important clue comes from the sediments deposited in ancient ocean basins. As mountains rise, erosion increases, sending large amounts of sediment into nearby seas. These sediments can pile up in thick layers, creating a record of the timing and intensity of uplift. By studying these layers, scientists can link the growth of mountains to the closing of oceans and the movement of plates. There is also a chemical record of these processes. The weathering of newly exposed rock can alter the composition of the atmosphere and oceans. For example, the breakdown of certain minerals can draw carbon dioxide out of the air, potentially cooling the climate over long periods. Large mountain-building events have been linked to global climate shifts in the geological record. This means that the rise of mountains and the opening and closing of oceans are not just local or regional events. They can influence the entire planet, shaping global patterns of climate and life. During the time when Pangea was coming together, these global effects were significant. The gradual elimination of ocean basins changed the way water circulated around the world. With fewer pathways for currents to move between hemispheres, the distribution of heat in the oceans shifted. This, in turn, affected atmospheric circulation, influencing weather patterns across the supercontinent. The vast interior of Pangea likely experienced more extreme conditions than the world does today. Far from the moderating influence of the oceans, temperatures could swing widely between seasons. Some regions may have been very dry, with large deserts forming in the heart of the landmass. Others, closer to the coasts or influenced by seasonal winds, may have seen periods of heavy rainfall. These conditions shaped the ecosystems that developed across the supercontinent. Plants and animals had to adapt to a wide range of environments, from coastal wetlands to arid interiors to mountainous regions. The connections between these regions allowed species to spread widely, but the differences in climate and terrain also created barriers and niches that encouraged diversity. The silence in between can be thought of as the background against which these larger changes played out. It is the steady, ongoing process of erosion, sedimentation, and slow uplift that continues even when no major plate boundary is nearby. It is the quiet accumulation of layers in a basin, the gradual smoothing of a landscape, the slow deepening or shallowing of a region as the mantle shifts beneath it. This quiet work is just as important as the dramatic events. Without it, there would be no record of the past to study, no layers of rock preserving fossils and climate indicators. The silence in between is what allows the planet to keep a memory of its own history. There is a certain balance to this system. Dramatic changes create new landscapes and new conditions. Quiet periods allow those landscapes to be shaped, stabilized, and recorded. Together they form a cycle that repeats over and over, each time leaving behind a different arrangement of land and sea. As scientists piece together the story of Pangea, they move back and forth between these different scales of change. They look at the big picture, the opening and closing of entire oceans, the rise of mountain chains that span continents. They also look at the small details, the grain of sand in a sedimentary layer, the fossil of a plant preserved in a quiet basin far from any plate boundary. Both perspectives are necessary. The large-scale movements provide the framework. The small-scale processes fill in the details, showing how those movements affected the surface of the world and the life that lived on it. Thinking about this can shift how you see the landscape around you. A mountain becomes more than a pile of rock. It becomes the crest of a slow wave that rose from a collision long ago. A flat plain becomes the product of millions of years of quiet deposition, layer upon layer of sediment settling in a place that was once under water or at the foot of a distant range. Even the ocean, which can feel timeless and unchanging, takes on a new character. Its floor is constantly being renewed, its shape altered by the creation and destruction of crust. The water above responds to these changes, flowing along new pathways, carrying heat and nutrients to different parts of the world. As the continents continued their slow approach during the era that would eventually give rise to Pangea, these processes intertwined in complex ways. Oceans narrowed and vanished. Mountains rose and were worn down. Quiet interiors recorded the passing of ages in layers of stone. The result was a world that was constantly changing, even in its moments of apparent stillness. The opening of an ocean in one place could, millions of years later, lead to the rise of a mountain range in another. The silence in between was never truly silent. It was filled with the steady, almost imperceptible work of a planet that never stops reshaping itself. With this understanding, the story of a united world becomes richer and more grounded. It is not just about continents coming together. It is about the countless processes that make such a gathering possible, and the equally powerful processes that ensure it will never last forever. As the last of the ancient oceans closed and the final mountain belts rose, the surface of the planet took on a form that would define a significant chapter in its history. The land was gathered, the seas were pushed to the edges, the interior stretched wide and deep, far from any coastline. Deep within the story of a world coming together, there is a chapter written not in gentle motion or quiet drift, but in heat, weight, and transformation. This is the part where the slow wandering of continents gives way to something more intense, where the surface of the planet is reshaped by forces that work from both above and below. Fire rises from the depths, pressure builds as land presses against land, and through this combination, an ancient supercontinent takes on its final form. To understand this stage, it helps to imagine what happens when two massive pieces of the Earth's crust finally meet after millions of years of closing distance. There is no soft landing. There is no simple merging of edges. Instead, there is a long, grinding encounter that can last for tens of millions of years. The rocks at the boundaries are squeezed, bent, and heated. Some are pushed deep into the earth, while others are forced upward, creating landscapes that can tower over everything around them. At the heart of this process is the energy stored in the moving plates themselves. Each plate carries momentum built up over vast spans of time as it drifts across the mantle. When two plates converge, that energy has to go somewhere. Much of it is absorbed by the deformation of the crust. Layers of rock that were once horizontal are folded like fabric. Faults slice through the ground, allowing blocks of crust to shift relative to one another. In some places, slabs of rock are stacked on top of each other, thickening the crust and pushing it higher into the atmosphere. As the crust thickens, the pressure at its base increases. The deeper parts of the rock are subjected to both high pressure and high temperature. Under these conditions, minerals can change their structure without melting. This process, known as metamorphism, transforms ordinary rock into new forms, often with distinctive textures and compositions. Shale can become slate, then schist, and eventually gneiss as it is buried deeper and heated more intensely. Limestone can turn into marble. Sandstone can become quartzite. These metamorphic rocks are like a record of the conditions they experienced. Their mineral arrangements can reveal the pressures and temperatures they were exposed to, allowing scientists to reconstruct the depth and intensity of ancient collisions. Finding these rocks at the surface today is a sign that they were once buried deep within the roots of a mountain range, and later brought back up by uplift and erosion. Fire enters the story through a different but closely related pathway. At many convergent boundaries, especially where an oceanic plate is involved, part of the crust is pushed down into the mantle. As it descends, it carries with it water and other volatile substances locked into the minerals of the rock. These substances lower the melting point of the surrounding mantle material, causing it to partially melt and form magma. This magma is less dense than the surrounding solid rock, so it rises. Sometimes it cools and solidifies underground, forming large bodies of igneous rock known as plutons. In other cases, it reaches the surface, erupting as lava and ash from volcanoes. Over time, repeated eruptions can build volcanic mountain ranges that run parallel to the site of subduction. These volcanic arcs often form along the edges of continents or as chains of islands in the ocean. They mark the line where one plate is sliding beneath another, tracing the boundary between two parts of the moving surface. During the assembly of Pangea, many such arcs formed, and were eventually caught up in the larger collisions that brought continents together. When a volcanic arc collides with a continent, it does not simply disappear. Its rocks, built up from layers of lava and ash, become part of the continental crust. This process, known as accretion, adds new material to the edge of a landmass, expanding it outward. Over time, repeated accretion events can significantly increase the size of a continent. This means that continents are not just drifting rafts. They're growing and changing as they move, collecting pieces of crust along the way. The final shape of Pangea was influenced not only by the positions of the original landmasses, but also by the many smaller fragments and arcs that were added during the long process of convergence. As these collisions and accretions continued, the surface of the planet became increasingly complex. Mountain belts formed in overlapping waves. Some ranges rose early in the process, only to be eroded and partially buried by later events. Others rose later, cutting across older structures and creating new patterns in the landscape. The weight of these growing mountain ranges had an effect that reached deep into the earth. Thickened crust is heavier than the surrounding areas, and this extra mass causes the underlying mantle to flow outward. This movement helps support the mountains, keeping them from sinking back down. It also influences how the surrounding regions rise or fall in response, creating basins where sediments can accumulate. These basins often form alongside mountain ranges, catching the material eroded from the rising peaks. Over time, they can fill with thick sequences of sediment, preserving a detailed record of the uplift and erosion of the nearby terrain. The layers in these basins can include river deposits, lake sediments, and even marine sediments if the area is flooded by the sea at some point. The presence of these sedimentary records allows scientists to trace the timing and progression of mountain building. By dating the layers and analysing their composition, they can see when erosion rates increased, when new sources of sediment appeared, and when the environment shifted from one type to another. This information helps tie the surface history of the land to the deeper processes of collision and uplift. Fire and pressure also play a role in shaping the chemistry of the crust. As magma rises and cools, it can concentrate certain elements, creating mineral deposits that can later become important resources. Metals like copper, gold, and iron are often associated with ancient volcanic and plutonic systems. The distribution of these resources today is, in part, a legacy of the tectonic and magmatic activity that accompanied the formation of supercontinents like Pangea. The climate of the planet does not remain untouched by these processes. Large-scale mountain building can influence atmospheric circulation. High ranges can block the movement of air masses, redirecting winds and altering rainfall patterns. The weathering of newly exposed rock surfaces can draw carbon dioxide out of the atmosphere, potentially leading to long-term cooling. During the assembly of Pangea, these effects likely combined in complex ways. The growth of vast mountain belts and the expansion of a single, massive landmass altered the balance of land and sea. Ocean currents changed. Atmospheric circulation patterns shifted. Some regions became wetter, others drier. Over millions of years, these changes influenced the distribution of ecosystems across the supercontinent. The interior of Pangea, far from any ocean, experienced conditions very different from those at the edges. Without the moderating influence of nearby water, temperatures could swing more widely between seasons. Rainfall patterns were more dependent on large-scale atmospheric movements, such as monsoon-like systems driven by the heating and cooling of the land. These environmental gradients created a wide range of habitats across the supercontinent. Coastal regions might support lush vegetation and diverse marine life. Interior basins could host deserts or grasslands. Mountainous areas provided cooler, wetter environments, with their own unique plant and animal communities. The movement of species across this connected landmass was shaped by these conditions. Some organisms could spread widely, following favourable environments across great distances. Others became restricted to specific regions, isolated by climate, terrain, or other barriers. This mix of connectivity and separation played a role in shaping the patterns of life preserved in the fossil record. As the final stages of Pangea's assembly unfolded, the last remaining ocean basins between the major land masses were gradually eliminated. The seafloor was consumed at subduction zones, and the continents on either side drew closer and closer. The volcanic arcs and fragments caught in between were squeezed, folded, and welded into the growing supercontinent. This phase of closure often leaves behind distinctive geological features. Long belts of deformed rock, known as suture zones, mark the lines where two continents once met. These zones can include pieces of ancient oceanic crust, fragments of volcanic arcs, and rocks that formed deep in the collision zone. They are the scars of the planet's efforts to stitch itself together. Finding and studying these suture zones is one of the ways geologists trace the boundaries of ancient landmasses. By mapping where these belts occur and dating the rocks within them, scientists can reconstruct the sequence of events that led to the formation of a supercontinent. In many cases, these zones are not obvious at the surface. They may be buried beneath the younger layers of rock or hidden within complex mountain ranges. It takes careful fieldwork combined with laboratory analysis to tease out their history. The final form of Pangea was the result of all these processes layered on top of one another. It was not a simple, smooth-edged continent. It was a patchwork of older cores, younger accreted fragments, and long belts of deformed and metamorphosed rock. Its interior was marked by ancient mountain ranges, some of which would later be worn down into plains and plateaus. Its edges were lined with active boundaries where new crust was being created and old crust was being destroyed. From a distance, it might have looked like a single, unified landmass. Up close, it would have been a complex and varied world, shaped by the long history of collisions, eruptions and transformations that brought it into being. There is a sense in which this stage of the story represents a peak of geological intensity. The forces that had been slowly drawing the continents together reached a kind of culmination. The last major collisions took place, the final sutures were sealed, the largest mountain belts rose to their greatest heights. Yet even at this moment of apparent completion, the processes that created Pangea were already setting the stage for what would come next. The thickened crust and deep roots of the mountain ranges altered the flow of heat from the mantle. The vast size of the supercontinent changed the way the planet lost heat to space. These changes would, over time, influence where the crust might weaken and begin to pull apart. In this way, the making of an ancient supercontinent is never truly separate from its eventual unmaking. Fire and pressure build the land up, but they also create conditions that can lead to its breakup. The same deep forces that bring continents together can, given enough time, push them apart again. From a human perspective, it can be tempting to see the formation of Pangea as a finished story, a dramatic event that happened long ago and is now over. But in the context of the planet's history, it is better understood as a phase in an ongoing cycle. Before Pangea, there were other supercontinents. After it, there will be more. Each one is shaped by the same fundamental processes: the movement of plates, the flow of heat, the interplay of fire and pressure. What changes are the details, the specific paths taken by the continents, the timing of collisions and separations, the particular landscapes that emerge and then fade. Thinking about this can shift the way you see the ground beneath you. It is not just a surface to walk on. It is part of a structure that has been built and rebuilt many times over, each time by the slow, persistent work of forces that operate far below our everyday awareness. The rocks beneath your feet may once have been part of a volcanic arc rising from an ancient ocean. They may have been buried deep in the roots of a mountain range formed during the assembly of Pangea. They may have been carried across the surface of the planet by a drifting plate, passing through different climates and environments along the way. Each of these possibilities is a reminder that the world we see is a snapshot in a much longer story. The making of Pangea was one of the grand chapters in that story, written in layers of lava, bands of metamorphic rock, and the folded remains of ancient seafloors. It leaves behind a sense of scale that can be both humbling and grounding. The fire and pressure that shaped an entire supercontinent are the same forces that continue to shape the planet today, even if their effects are less obvious on the timescale of a human life. With the land now gathered and the major collisions complete, the stage is set for a different kind of exploration. What was it like to live on a world where the continents were united, where land stretched for thousands of kilometers without a break, and where the rhythms of climate and life were shaped by a single, massive landmass? To imagine life on a world without edges, it helps to let go of the mental map you carry of oceans dividing continents and coastlines, marking clear boundaries between land and sea. Instead, Picture a vast, continuous surface of ground stretching so far in every direction that the idea of the other side of the world loses much of its meaning. On Pangea, there were no familiar ocean crossings separating distant lands. There was land connecting regions that are now divided by thousands of kilometres of water. For the plants and animals that lived there, this continuity shaped nearly every aspect of their existence. The absence of major ocean barriers meant that movement across the supercontinent was, in principle, much easier than it is today. Species that could travel over land had the potential to spread across enormous areas, following rivers, plains, forests and coastlines that all belong to the same connected system. Over long periods, this created patterns of life that look very different from what we see in the modern fragmented world. In today's geography, oceans often act as powerful isolating forces. They separate populations, limit the movement of species, and create distinct biological regions. On Pangea, that kind of isolation was less common across the land itself. Instead, the main barriers were shaped by climate, terrain, and distance rather than by water. Mountain ranges, deserts, and vast interior regions played roles similar to oceans in determining where life could thrive and where it struggled to cross. One of the most influential factors in shaping life on Pangea was the sheer size of the landmass. With so much land gathered together, the interior of the supercontinent lay far from any coastline. This distance from the ocean had profound effects on climate, and those climate patterns in turn shaped ecosystems. Near the coasts, conditions were often moderated by the presence of the sea. Temperatures tended to be more stable, and moisture from the ocean could fall as rain, supporting lush vegetation in many regions. These coastal environments likely resembled the kinds of productive ecosystems we see along modern shorelines, with a mix of forests, wetlands, and shallow marine habitats. Farther inland, the story was different. As air masses moved across the vast expanse of land, they lost much of their moisture before reaching the centre of the supercontinent. This created large regions that were relatively dry, with more extreme temperature swings between seasons. Hot summers and cold winters were more common in these interior areas, and rainfall was less predictable. These conditions favoured certain types of plants over others. In many places, hardy, drought-tolerant vegetation would have dominated, such as early seed plants and tough, low-growing species that could survive long dry periods. Along rivers and in low-lying areas where water collected, more lush plant communities could develop, creating green corridors that cut through otherwise dry landscapes. These corridors were important for animals as well. Rivers and wetlands provided reliable sources of water and food, making them natural pathways for movement across the supercontinent. Over time, these routes could connect distant regions, allowing species to spread widely and mix with populations far from their point of origin. The fossil record reflects this kind of connectivity. Similar species of plants and animals appear in rock layers that are now found on different continents. On Pangea, these regions were part of the same landmass, so their shared life forms make sense in a way that would be difficult to explain in today's separated world. One of the most well-known examples is the distribution of certain early reptiles and amphibians. Fossils of the same or closely related species have been found in areas that are now separated by oceans, such as parts of what we call South America, Africa, and North America. These animals were land dwellers or lived in freshwater environments. They did not have the ability to cross wide seas. Their presence in these different regions points to a time when those lands were connected, allowing the animals to move freely across them. Plants tell a similar story. The ancient seed fern Glossopteris, for instance, left its distinctive leaves preserved in rocks across much of what is now the southern hemisphere. On Pangea, these regions were joined together, forming a continuous area where this plant could spread and thrive. Its widespread presence suggests that large parts of the supercontinent shared similar climates and ecosystems during certain periods. The connected nature of the land also influenced how species evolved. When populations can move and mix over large areas, it can slow down the process of divergence, where new species form from isolated groups. On Pangea, some species likely maintained large, interconnected populations across wide regions, which could have kept them relatively uniform over long periods. At the same time, the supercontinent was far from uniform. Its size and varied geography created many different environments. Mountain ranges formed by continental collisions created cooler, wetter conditions at higher elevations. Lowland basins collected water and sediments, forming wetlands, lakes, and shallow inland seas. Deserts spread across dry interior regions. Coastal zones experienced the influence of tides and marine currents. These varied habitats provided opportunities for specialization. Even in a connected landmass, species could become adapted to specific environments and remain largely confined to them. A plant that thrived in a swampy lowland might not survive on a dry plateau. An animal adapted to cooler mountain climates might not cross a hot, arid plain. In this way, the supercontinent still supported a rich mosaic of life, shaped by environmental boundaries rather than by oceans. The size of Pangea also influenced global patterns of climate in ways that affected life everywhere. With so much land gathered together, the balance between land and sea on the planet was very different from what it is today. This affected how heat was absorbed and released, how winds circulated, and how rain fell. Large land areas heat up and cool down more quickly than oceans. This can create strong seasonal differences in temperature. On Pangea, these effects were likely amplified, especially in the interior. Seasonal winds may have developed that brought moisture to some regions at certain times of year and left them dry at others, similar to modern monsoon systems, but potentially operating on a much larger scale. These seasonal patterns would have shaped the life cycles of plants and animals. Many species would have timed their growth, reproduction, and movement to match periods of rain or warmth. Fossil evidence such as growth rings in ancient trees and patterns in sediment layers suggests that some regions experienced strong seasonal changes during the time of the supercontinent. The oceans around Pangea also played a role in shaping life, even though they were pushed to the edges of the landmass. The configuration of the supercontinent altered ocean currents, which in turn affected marine ecosystems. Some regions of the surrounding seas may have experienced reduced circulation, leading to lower oxygen levels in the water. This could create challenging conditions for marine life and influence where different species could survive. Shallow seas along the edges of the supercontinent were often rich in nutrients, supporting diverse communities of marine organisms. Coral-like structures, shellfish, and early fish thrived in these environments. The remains of these communities were preserved in limestone and other sedimentary rocks that can still be found today in places far from modern coastlines. Life on land and life in the sea were not completely separate. Rivers carried nutrients from the interior of the supercontinent to the coasts, feeding coastal ecosystems. At the same time, changes in sea level could flood low-lying areas of the land, creating temporary marine environments that later became part of the terrestrial record. The long stretches of connected land also influenced how mass extinctions and recoveries played out. When a major environmental change occurred, such as a shift in climate or a drop in oxygen levels in the oceans, its effects could spread across large areas of the supercontinent. This could lead to widespread declines in certain species. On the other hand, the connectivity of the land could also aid recovery. Surviving populations in one region could spread into areas where species had disappeared, helping to repopulate ecosystems. This dynamic of loss and recolonization is visible in the fossil record, where periods of decline are often followed by the appearance of new or returning species across wide regions. The interior of Pangea likely hosted some of the most extreme environments. Large deserts may have formed in areas far from any source of moisture. These regions would have been challenging places for life, favouring species that could conserve water and withstand temperature extremes. Evidence for these ancient deserts comes from certain types of rock formations, such as large cross-bedded sandstones that resemble the deposits formed by windblown dunes today. Fossils in these layers are often sparse, reflecting the difficulty of surviving in such conditions. Yet even in these harsh environments, life found ways to persist. Some plants developed thick cuticles and deep root systems to access scarce water. Animals may have adopted behaviours such as burrowing or nocturnal activity to avoid the worst heat of the day. These adaptations left subtle traces in the fossil record, offering glimpses into how organisms coped with the challenges of a vast dry interior. Closer to the coasts and in wetter regions, ecosystems were likely more diverse and productive. Forests of early trees and seed plants provided habitat for a range of insects, amphibians and reptiles. Rivers and lakes supported fish and other aquatic life, as well as animals that moved between water and land. The absence of major ocean barriers also meant that diseases, parasites and other biological pressures could spread over large areas. This would have influenced the evolution of immune responses and other survival strategies in ancient species. The supercontinent was not just a place of opportunity, it was also a place of competition, where species had to contend with a wide array of rivals and challenges across a connected landscape. The scale of the landmass also affected the way nutrients were cycled. In modern times, oceans play a major role in distributing nutrients around the planet. On Pangea, with more land and relatively enclosed seas, the balance of nutrient flow was different. Large river systems may have been especially important in carrying minerals and organic material from the interior to the coasts. These rivers could stretch for thousands of kilometres, crossing multiple climate zones and collecting water from vast drainage basins. Along their banks, rich soils supported dense plant growth, which in turn supported a variety of animals. The floodplains of these ancient rivers were likely hotspots of biodiversity within the broader, often drier supercontinent. Fossils preserved in these river and floodplain deposits provide some of the most detailed snapshots of life on Pangea. They include the remains of plants, insects, amphibians, reptiles, and early ancestors of mammals. Together, they paint a picture of ecosystems that were both familiar and alien, shaped by conditions that no longer exist in quite the same way. The connected nature of the land also influenced the spread of evolutionary innovations. When a new trait or adaptation appeared in one region, it could, over time, spread across much of the supercontinent if the environment allowed. This could lead to relatively rapid changes in the makeup of ecosystems over large areas. At the same time, the size and complexity of Pangea meant that not all regions experienced the same changes at the same time. Local conditions still mattered. A mountain range could block the spread of a species. A desert could form a barrier that separated populations. A shift in climate could open up new pathways in one area while closing them in another. This combination of connectivity and diversity made life on Pangea both widespread and varied. It was a world where some species could range across enormous distances, while others were confined to specific niches. Thinking about this kind of world can feel strange because it challenges the way we usually imagine geography and biology. We are used to thinking in terms of continents as separate arenas, each with its own distinct sets of plants and animals. On Pangea, those arenas were merged into a single sprawling stage. This does not mean that the world was uniform or simple, quite the opposite. The supercontinent's size and complexity created a wide array of environments and evolutionary pressures. The difference is that these environments were all part of one connected system, rather than being separated by vast stretches of ocean. The fossil record preserves this interconnectedness in subtle ways. Similar species appear across wide regions. Related groups of animals and plants show patterns of distribution that make sense only when you imagine a continuous landmass. These patterns become harder to explain once the continents break apart and oceans form between them. As Pangea began to reach its most complete form, the balance between land and sea, connectivity and separation, stability and change, created a unique set of conditions for life. Some lineages flourished and spread widely. Others struggled or disappeared. New forms emerged, adapted to the particular challenges and opportunities of a world without familiar edges. The legacy of this period is still with us. the distribution of certain groups of plants and animals today reflects ancient connections that date back to the time of the supercontinent. Even though the land has since broken apart, those historical links can still be traced in genetic relationships and fossil records. This sense of continuity across deep time can change the way you look at the natural world. A plant in one part of the world may have distant relatives on another continent, not just because of recent movement or human influence, but because their ancestors once shared a home on a single ancient landmass. When you imagine the climate of a world shaped by a single endless land, it can help to start with something familiar and then slowly stretch it beyond its usual limits. Think of how different the weather feels near a coastline compared to deep inland. Near the sea, temperatures tend to be softer, changes between day and night less dramatic, and the air often carries more moisture. Far from the water, those moderating influences fade. Heat and cold arrive more sharply. Rain becomes less predictable. Now take that contrast and extend it across a landmass so large that some regions are thousands of kilometres from the nearest ocean. That was the stage on which the climate of Pangea played out. The first thing to understand is the role of water in shaping temperature. Oceans and large bodies of water absorb heat slowly and release it slowly. This makes them powerful stabilizers of climate. They keep coastal regions from heating up too quickly during the day or cooling down too sharply at night. They also soften the extremes between seasons, storing warmth during the summer and giving some of it back during the winter. On a supercontinent, much of the land lies far beyond the reach of this influence. The interior of Pangea was, in many places, isolated from the oceans by sheer distance. Air masses travelling inland would lose much of their moisture as rain along the coasts and mountain ranges. By the time they reached the heart of the landmass, they were often dry, and the climate they delivered reflected that. This created large continental interiors with strong seasonal contrasts. Summers could be very hot, as the land absorbed solar energy quickly, and there was little nearby water to moderate the temperature. Winters could be cold, especially in regions that lay at higher latitudes or elevations. The swing between these extremes shaped not just daily weather, but long-term patterns of life and geology. The size and shape of Pangea also influenced the movement of air around the planet. Wind patterns are driven by differences in temperature and pressure between different regions of the Earth's surface. Warm air rises, creating areas of lower pressure, while cooler air sinks, creating higher pressure. The atmosphere responds by moving air from high-pressure areas toward low-pressure areas, creating the winds that carry heat and moisture around the globe. On a world with many separate continents and wide oceans, these patterns are broken up and redirected by the presence of water and land in different places. On Pangea, the large continuous landmass allowed some of these patterns to develop on a much larger scale. One likely feature of Pangea's climate system was the presence of strong continent-wide monsoon-like circulations. During the warmer months, the vast landmass would heat up more quickly than the surrounding oceans. This would cause air over the land to rise, creating a large area of low pressure. Moist air from the oceans would be drawn inland to replace it, bringing rain to coastal and near-coastal regions. As this moist air moved farther inland, it would cool and lose much of its water as precipitation. By the time it reached the interior, there would be little moisture left to fall as rain. This pattern could create a gradient of wet conditions near the edges of the supercontinent and much drier conditions toward the centre. During the cooler months, the pattern could reverse. The land would cool more quickly than the oceans, creating high-pressure areas over the interior. Air would flow outward toward the sea, reducing rainfall over much of the land. This seasonal switching could produce distinct wet and dry periods, similar in principle to the modern monsoon systems, but operating over a much larger area. These broad patterns were further shaped by the position of Pangea on the globe. At different times in its history, parts of the supercontinent lay near the equator, while others extended into higher latitudes. This meant that different regions experienced very different levels of solar heating. Near the equator, sunlight strikes the surface more directly throughout the year. This tends to create warm temperatures and can support the development of tropical climates, especially where moisture is available. In these regions of Pangea, warm conditions combined with seasonal rainfall could support dense vegetation, including forests and wetlands. Farther from the equator, the angle of sunlight changes more over the course of the year. Summers can be warm, but winters can be much colder. In these regions, the climate of Pangea likely included more pronounced seasons, with shifts in vegetation and animal activity tied closely to the changing temperatures and availability of water. The presence of large mountain ranges added another layer of complexity. Mountains act as barriers to moving air. When moist air encounters a rising slope, it is forced upward. As it rises, it cools, and the moisture it carries can condense and fall as rain or snow. This often leads to wetter conditions on the side of the mountain facing the incoming wind, and drier conditions on the opposite side, in what is known as a rain shadow. On Pangea, long mountain belts formed along the lines where continents collided. These ranges could stretch for thousands of kilometers. Their influence on climate would not have been limited to their immediate surroundings. By redirecting winds and shaping where rain fell, they could affect conditions across vast regions. For example, a mountain range near the coast could block moist air from moving inland, creating a dry interior basin. Conversely, a range positioned differently could channel winds in a way that brought seasonal rains deep into the landmass. The exact effects would have depended on the shape and orientation of the mountains, as well as the broader circulation patterns of the atmosphere. The distribution of deserts on Pangea offers some insight into these processes. Geological evidence suggests that large arid regions existed in the interior of the supercontinent at various times. These areas are marked in the rock record by features such as windblown sand deposits and evaporate minerals, which form when water bodies dry up and leave behind concentrated salts. The formation of these deserts reflects the combined influence of distance from the ocean, prevailing wind patterns, and the presence of mountain barriers. With little moisture reaching these regions, vegetation would have been sparse, and erosion by wind rather than water would have played a larger role in shaping the landscape. At the same time, not all interior regions were uniformly dry. Large river systems could carry water far from the coasts, creating corridors of more hospitable conditions through otherwise arid areas. These rivers would have been fed by rainfall in wetter regions, such as coastal zones or mountain slopes, and could support floodplains and wetlands along their courses. The paths of these rivers were shaped by the overall tilt and structure of the land. As Pangea formed, the collisions and thickening of the crust created high regions and basins. Water flowed downhill from these high areas, carving channels that could persist for millions of years. The sediments they carried built up in low-lying regions, creating layers of rock that now preserve evidence of ancient climates and ecosystems. The oceans surrounding Pangea were also influenced by the shape of the supercontinent. With much of the land gathered into a single mass, the major ocean basins were arranged differently than they are today. This affected the way water circulated around the globe. Ocean currents play a key role in transporting heat from one region to another. Warm water from the equator can flow toward the poles, while cold water moves back toward lower latitudes. These currents help regulate global climate, making some regions warmer and others cooler than they would otherwise be. The presence of a supercontinent can disrupt or redirect these flows. Narrow seaways between parts of the landmass can act as bottlenecks, limiting the movement of water between different ocean basins. If a current is blocked or weakened, the distribution of heat can change, leading to shifts in climate both on land and at sea. During the time of Pangea, some ocean basins may have experienced reduced circulation, especially in areas where the land formed nearly continuous barriers. This could lead to lower oxygen levels in deeper waters, creating challenging conditions for marine life. Evidence of such conditions can be found in certain types of sedimentary rocks that form in low oxygen environments. At the same time, shallow seas along the edges of the supercontinent could be highly productive. Nutrients carried by rivers from the land would flow into these coastal waters, supporting rich ecosystems of algae, invertebrates, and early fish. The remains of these organisms were often preserved in limestone and other marine sediments, which now appear far inland due to later tectonic movements. Another important aspect of Pangea's climate involves the long-term balance of gases in the atmosphere, particularly carbon dioxide. The concentration of this gas plays a major role in regulating the planet's temperature as it traps heat in the atmosphere. The movement of continents and the formation of large landmasses can influence this balance in several ways. One of the most significant is through chemical weathering. When rain falls on rocks, it can react with certain minerals, breaking them down and forming new compounds. This process can remove carbon dioxide from the atmosphere and lock it into solid materials that eventually become part of sedimentary rocks. On a supercontinent, especially in warm and wet regions, the scale of this process can be very large. Vast areas of exposed rock can be subject to weathering, potentially drawing down significant amounts of carbon dioxide over millions of years. This can contribute to long-term cooling of the planet. At the same time, volcanic activity associated with plate boundaries and mantle processes can release carbon dioxide back into the atmosphere. During the assembly of Pangea, there were many active collision zones and volcanic arcs, which would have added gases to the air. The balance between these two processes, weathering removing carbon dioxide and volcanism adding it, helps shape the planet's long-term climate. Shifts in this balance can be recorded in the geological record as periods of warming or cooling. There is evidence that parts of the time when Pangea existed were marked by large-scale glaciations, especially in the southern regions of the supercontinent. Glacial deposits have been found in rocks that now lie in areas that are far from the poles. These deposits suggest that ice sheets once covered parts of Pangea that were located at higher latitudes. The presence of such ice sheets would have had a strong influence on global climate. Ice reflects sunlight, which can lead to further cooling in a feedback process. As ice expands, more sunlight is reflected, temperatures drop further, and more ice can form. This kind of feedback can lead to extended periods of cooler climate. The arrangement of the supercontinent could have contributed to these conditions. Large land areas at higher latitudes, combined with changes in atmospheric circulation and ocean currents, may have made it easier for ice sheets to form and persist. At lower latitudes, the climate story was different. Warm temperatures and, in some regions, seasonal rainfall supported extensive vegetation. Fossil evidence suggests the presence of large swampy areas during certain periods, where dense plant growth led to the formation of thick layers of organic material. Over time, these layers were buried and transformed into coal. The distribution of coal deposits today reflects the past positions of continents and climate zones. Coal beds found in regions that are now temperate or even cold often formed when those regions lay closer to the equator, under warm, wet conditions. This is another example of how the movement of land across the globe can leave a lasting imprint on the geological record. The scale of Pangea also influenced how quickly climate changes could spread across the land. On a smaller continent, a shift in ocean currents or atmospheric patterns might primarily affect one region. On a supercontinent, the same kind of shift could have far-reaching effects, influencing weather patterns across thousands of kilometers. This could make the climate of Pangea both stable in some ways and vulnerable in others. The large size of the landmass could buffer certain regions from short-term fluctuations, but when a major change did occur, its effects could be widespread. Life on Pangea had to adapt to this dynamic climate system. Plants and animals evolved strategies to cope with seasonal changes, long dry periods, and temperature extremes. Some species developed the ability to go dormant during unfavourable conditions. Others evolved physical traits that helped them conserve water or regulate their body temperature. These adaptations are visible in the fossil record. Growth rings in ancient trees can indicate seasonal patterns of rainfall and temperature. The shapes of leaves can suggest whether plants grew in warm, wet environments or in drier, cooler ones. The structure of animal bones and teeth can hint at their diets and the kinds of environments they lived in. By combining this biological evidence with geological and chemical data, scientists can reconstruct a picture of Pangea's climate that is both detailed and complex. It was not a single, uniform environment, but a patchwork of regions, each shaped by its position on the supercontinent and its relationship to the oceans and mountains around it. There is also an important sense in which the climate of Pangea was a transitional phase in the planet's history. The formation of the supercontinent marked a shift in the balance between land and sea, between connectivity and separation. This shift had long-term consequences for how heat and moisture were distributed around the globe. As the supercontinent later began to break apart, new ocean basins opened. These changes allowed ocean currents to flow in new ways, altering global climate patterns once again. The transition from a world dominated by a single landmass to one with multiple continents separated by wide oceans reshaped the planet's climate in ways that are still being felt today. Thinking about this can add a sense of depth to everyday experiences of weather and climate. The patterns of wind and rain, of hot and cold, are not just the result of immediate conditions. They are part of a system that has been shaped by the movement of continents over hundreds of millions of years. The climate of a single, endless land is a reminder of how closely linked the different parts of the Earth system are. The deep interior of the planet influences the movement of plates. The movement of plates shapes the arrangement of land and sea. That arrangement influences the flow of air and water, and those flows shape the conditions under which life evolves and landscapes form. This chain of connections stretches across vast spans of time and space, linking the heat rising from the mantle to the rain falling on a distant plain, the collision of continents to the growth of a forest. As the story of Pangea continues, this interconnectedness becomes even more apparent. The climate that developed on the supercontinent played a role in shaping the stresses within the land itself. Changes in erosion, sedimentation, and the weight of ice and water could influence how the crust responded to the deep forces beneath it. In this way, the atmosphere and the lithosphere, the air and the rock, were not separate realms. They were parts of a single evolving system. At first, nothing looks different. The land still stretches wide. The mountains still cast their long shadows. Rivers still follow their ancient paths toward distant seas. From the surface, the world appears as solid and unified as it has for millions of years. Yet beneath that familiar stillness, something begins to change. The balance that once held the vast landmass together starts to shift, not in any dramatic or sudden way, but through a slow accumulation of stress and heat that quietly prepares the ground for a new phase in the planet's long cycle. To understand how cracks can form in something as enormous as a supercontinent, it helps to return to the deep interior of the Earth. The mantle beneath the crust never truly stops moving. Heat continues to rise from below, flowing in broad, slow currents that respond to the shape and weight of the land above. When a massive landmass like Pangea sits over a large area of the mantle, it changes how that heat escapes. Thick continental crust acts like an insulating layer. It slows the release of heat from the mantle to the surface. Over long periods, this can lead to a build-up of warmth beneath the supercontinent. The rocks below become hotter, and as they heat up, they become slightly less dense and more buoyant. This can cause them to rise, forming broad domes of uplift in the overlying crust. From the surface, this uplift might be almost imperceptible at first. A plain rises by a few meters. A river's gradient changes slightly. Drainage patterns shift as water finds new paths downhill. These small changes, spread across millions of years, can alter entire landscapes without any single moment of drama. As the crust is lifted and heated from below, it also begins to stretch. Rock, even solid rock, can deform when enough force is applied over a long enough time. The upper layers of the crust respond by developing fractures and faults, zones where the rock begins to break or slide. These early cracks are often subtle. They may appear as long, shallow valleys, aligned in roughly parallel patterns. Geologists call these features rifts, and they mark places where the crust is being pulled apart. At this stage, the land is still connected. The cracks do not yet reach deep enough to create new ocean basins. They are more like the first lines in a piece of fabric that is being gently, steadily stretched. Volcanic activity often accompanies this stretching. As the crust thins, it becomes easier for magma from the mantle to rise toward the surface. In some places, this magma pools underground, forming large bodies of igneous rock. In others, it erupts, creating chains of volcanoes along the developing rift. These volcanic regions can leave behind distinctive layers of rock built up from repeated flows of lava and deposits of ash. Over time, these layers can form broad plateaus, sometimes covering areas as large as modern countries. The presence of these volcanic provinces in the geological record is one of the clues scientists use to identify periods of rifting and continental breakup in the past. As the rift continues to develop, the land on either side may begin to sink slightly, creating a central valley. Lakes can form in these low-lying areas, collecting water from the surrounding high ground. Rivers may change course, flowing into the rift rather than toward their previous outlets. Sediments carried by these rivers begin to fill the valley, creating thick layers of sand, mud, and organic material. These sediments tell their own story. They can preserve fossils of plants and animals that lived along the rift, providing a snapshot of the ecosystems that existed during the early stages of continental breakup. They also record changes in water levels, climate, and volcanic activity, all of which can be tied back to the deeper processes at work beneath the surface. While these changes unfold in one region, other parts of the supercontinent may remain relatively stable. The formation of cracks does not happen everywhere at once. It tends to focus along zones of weakness in the crust, areas that were shaped by earlier collisions, mountain-building events, or ancient plate boundaries. These inherited structures act like faint lines in a piece of wood, guiding where it is most likely to split when pressure is applied. The scars of past tectonic events become the pathways for future ones. In this way, the history of the continent influences its future, linking different phases of the supercontinent cycle into a continuous narrative. As rifting progresses, the crust can become thin enough that magma from the mantle reaches the surface more directly. When this happens, new crust begins to form in the gap. At first, this crust is continental in character, made from volcanic and sedimentary rocks. But as the rift widens and deepens, the nature of the crust can change. Eventually, the rift may become a narrow sea. Water floods into the low-lying region from the surrounding ocean. The environment shifts from terrestrial to marine. New types of sediments are deposited, including marine sands, muds, and the remains of ocean-dwelling organisms. The once connected land is now divided by a body of water, even if it is still small compared to a full ocean. This transition marks a significant turning point. The process that once brought continents together now begins to pull them apart. The same forces of heat and movement that guided the assembly of the supercontinent are now driving its separation. The birth of a new ocean basin is a gradual affair. At first, the sea may be shallow and narrow, more like a long, winding gulf than an open ocean. Over time, as new crust continues to form at the centre of the basin and older crust moves outward, the basin widens. The continents on either side are carried away from each other by the slow, steady motion of their plates. This widening can continue for tens of millions of years, transforming a modest rift into a vast ocean. The Atlantic Ocean, for example, began as a series of rifts within the supercontinent that would later become Pangea. Those rifts eventually connected, filled with water, and grew into the broad ocean that now separates the Americas from Europe and Africa. While some regions are being pulled apart, others may still be experiencing the effects of earlier collisions. Mountain ranges that formed during the assembly of the supercontinent can continue to rise for a time, even as the land begins to break elsewhere. The planet's surface can, for a while, display both the scars of union and the signs of separation at the same time. This overlapping of processes creates a complex and dynamic landscape. In one area, land is stretching and cracking. In another, it is still thickening and rising. Rivers may be carving valleys into ancient mountains while new seas are opening nearby. The world becomes a patchwork of different geological stories, all unfolding in parallel. The development of cracks in the supercontinent also has far-reaching effects on climate and life. As new seas form, they create new coastlines. These coastlines become zones of interaction between land and ocean, often rich in nutrients and biodiversity. The presence of water moderates temperatures, leading to milder climates in nearby regions. At the same time, the opening of new ocean basins can alter global patterns of ocean circulation. Currents that once flowed around the edges of a single landmass can now pass through new pathways. This redistribution of heat and nutrients can lead to changes in climate far from the site of the rift. The interior of the landmass, now smaller and less isolated, may begin to experience more moderate conditions as the influence of the oceans extends farther inland. Regions that were once dry and extreme can become wetter and more temperate. These shifts can open up new habitats and migration routes for plants and animals. The breaking of the land also changes how species are distributed. As water barriers form, populations that were once connected can become isolated. Over time, this isolation can lead to the development of new species, as groups adapt to their local environments without mixing with others. This process of separation, known as vicariance, is a powerful driver of biodiversity. It is one of the reasons why different continents today host distinct sets of plants and animals, even when they share similar climates. The fossil record captures this transition in subtle ways. In older layers, you may find the same species or closely related ones spread across wide regions of what was once a continuous landmass. In younger layers, after rifting has begun, those patterns start to change. Distinct regional forms appear, reflecting the growing separation between populations. There's also a record of environmental change preserved in the rocks of rift basins and young oceans. Layers of sediment can show shifts from river and lake deposits to marine deposits, marking the moment when seawater first entered a region. Changes in fossil assemblages can reveal how ecosystems responded to the new conditions. Volcanic rocks associated with rifting often contain clues about the composition of the mantle and the nature of the heat sources driving the process. By analysing these rocks, scientists can gain insight into what was happening deep beneath the surface during the early stages of continental breakup. These deep processes are not always steady. The flow of heat and material in the mantle can change over time, influenced by the movement of plates and the sinking of old crust at subduction zones. A region that experiences rifting for a period may later become stable again, while rifting begins elsewhere. This means that the breakup of a supercontinent is not always a simple, clean division. It can involve a series of starts and stops, with some rifts failing to develop into full ocean basins. These failed rifts can leave behind long, narrow valleys and basins that persist as features in the landscape, long after the main breakup has moved on. Such features can often be recognised in the modern world. Some large river valleys and lowland regions trace the paths of ancient rifts that never fully opened into oceans. They are reminders of past attempts by the planet to pull the land apart, attempts that were redirected or abandoned as the balance of forces shifted. As the cracks in the Great Hole continue to develop, the shape of the landmass changes in ways that can be traced on a map. Peninsulas grow longer, seas cut deeper into the interior, islands form along the edges of new basins. The once simple outline of the supercontinent becomes more intricate, marked by bays, straits, and emerging ocean margins. These changes have cultural and ecological significance in a broader sense, Even though no humans were present to witness them at the time, they set the stage for the future arrangement of continents, for the positions of coastlines, and for the pathways along which life would later spread. In the context of the planet's long history, this phase of cracking and separation is as important as the earlier phase of collision and assembly. Together, they form two halves of a larger cycle, a rhythm of coming together and pulling apart that has repeated many times over billions of years. What makes this cycle particularly fascinating is that it is not perfectly regular. The timing, the locations, and the outcomes of each phase vary. The supercontinents of the past were not identical to each other, and the ones of the future will not simply repeat the pattern of Pangea. Each iteration reflects the specific conditions of the mantle, the arrangement of plates, and the accumulated history of the crust at that time. The cracks that form in a supercontinent are therefore not just signs of its end. They are also the beginnings of something new. Each rift that opens has the potential to become an ocean, a boundary between future continents, and a driver of new climate and biological patterns. From a certain perspective, this makes the surface of the planet feel less like a stable foundation and more like a living, evolving system. The land you stand on is part of a structure that has been assembled and disassembled many times before and will continue to change long into the future. As the story of Pangea moves forward, these early cracks grow wider. The narrow seas expand. The landmasses on either side drift farther apart. The once unified world begins to take on a shape that starts to resemble the familiar arrangement of continents we recognize today. But this transformation is not complete or simple. It unfolds in stages, with periods of rapid change and long intervals of relative calm. Some regions separate quickly, others remain connected for much longer, forming bridges between emerging continents. Following these pathways of separation reveals how the modern world took shape from the ancient whole. It shows how the placement of oceans, the orientation of continents, and the distribution of climates and ecosystems are all linked back to these early fractures in the land. By the time the first clear separations began to take shape, the world had already been whole for a long stretch of geological time. The land had settled into its vast, connected form. Rivers had carved their paths across enormous distances. Ecosystems had adapted to the rhythms of a single, sprawling continent. From the perspective of the planet, Pangea had reached a kind of maturity, and yet beneath that sense of stability, the forces that had brought everything together were quietly guiding the next phase of the story. The long goodbye did not arrive with a single dramatic moment. There was no sudden tearing of the land, no instant appearance of oceans where plains had been. Instead, separation unfolded in a way that mirrored assembly, slow, uneven, and deeply shaped by the history that came before it. Some regions began to pull apart early. Others held on for tens of millions of years longer, maintaining connections even as seas widened nearby. One of the defining features of this phase is how asymmetrical it was. The supercontinent did not split neatly down the middle. Instead, it fractured along a network of rifts that followed older lines of weakness in the crust. These weaknesses often traced the boundaries of ancient collisions, mountain belts, and sutures, where land masses had once been stitched together. The scars of Pangea's formation became the pathways of its unmaking. As rifting continued in certain regions, narrow seas widened into young oceans. The crust at the centre of these basins was fresh and warm, created from rising mantle material that cooled and solidified as it reached the surface. On either side, the continental edges began to develop the familiar features of passive margins, broad continental shelves, gentle slopes, and thick accumulations of sediment carried by rivers from the land. These new coastlines marked a profound change in how the planet functioned. Where there had once been vast interior regions far from any ocean, water now reached deeper into the land. The moderating influence of the sea began to soften climates in areas that had previously experienced more extreme conditions. Rainfall patterns shifted. Rivers adjusted their courses to meet new outlets. Wetlands formed along emerging shores. The opening of these new basins also transformed the oceans themselves. Water that had once circulated around the edges of a single landmass now flowed through growing gaps between separating continents. These new pathways allowed currents to redistribute heat and nutrients in different ways, gradually reshaping global climate patterns. At the same time, the breakup of Pangea did not happen everywhere at once. While some regions were stretching and thinning, others were still experiencing the aftereffects of earlier collisions. Mountain ranges continued to rise in places where the crust was still thickening. Erosion worked on peaks that had formed millions of years earlier, carrying their material into basins and young oceans. This overlapping of processes created a world in transition. It was neither fully united nor fully separated. It was a patchwork of connected and disconnected regions, of old mountains and new seas, of stable interiors and active boundaries. One of the earliest major separations involved what would eventually become the northern and southern halves of the supercontinent. A broad zone of rifting developed, gradually dividing the land into two large blocks often referred to as Laurasia in the north and Gondwana in the south. The sea that opened between them was an early ancestor of parts of today's Atlantic and Tethys oceans. As this divide widened, it created new opportunities and challenges for life. Populations of plants and animals that had once been part of a continuous range found themselves separated by growing stretches of water. Over time, these isolated groups began to follow their own evolutionary paths, shaped by the specific conditions of their new homes. The fossil record reflects this divergence. Species that were once widespread across large areas of the supercontinent began to appear in more restricted regions. New forms emerged that were adapted to local climates and environments. The breakup of the land acted as a kind of evolutionary experiment, creating multiple, separate stages on which life could evolve in different directions. The long goodbye also involved the gradual rotation and movement of individual land masses. As plates continued to drift, continents did not simply move straight away from each other. They turned, pivoted, and followed curved paths across the surface of the planet. These movements shaped the orientation of future coastlines and the relative positions of emerging continents. For example, what would become Africa began to rotate slightly as it moved away from the land that would form the Americas. This rotation influenced the shape of the Atlantic basin and the alignment of mountain ranges and sedimentary basins along the new coasts. South America too followed a curved path, gradually shifting westward and southward as the Atlantic widened. Meanwhile, in the eastern part of the world, other changes were underway. The vast ocean that lay between the northern and southern landmasses, often referred to as the Tethys, began to change shape as smaller blocks of crust drifted across it. These fragments, sometimes called microcontinents, moved like rafts across the ocean, eventually colliding with larger land masses. These collisions created new mountain ranges and reshaped coastlines, adding complexity to the breakup process. The formation of regions that would later become parts of Europe, the Middle East and Asia involved a series of such events, each one leaving behind belts of deformed rock and layered histories. The presence of these moving fragments highlights another aspect of the long goodbye. The breakup of a supercontinent does not always produce only large, cleanly separated continents. It can also generate a scattering of smaller pieces, each with its own journey and its own role in shaping the future world. These fragments can travel long distances before finding a new home. As they move, they interact with ocean currents, climate patterns, and biological distributions. When they finally collide with a larger continent, they can bring with them species, sediments, and geological features from their place of origin, adding new layers to the story of the land they join. The widening of oceans during this phase also changed the balance of forces acting on the plates. As new seafloor formed at mid-ocean ridges, it pushed the continents farther apart. At the same time, subduction continued along other boundaries, where old oceanic crust was being consumed. This meant that while some parts of the world were opening, others were closing. The planet's surface remained a dynamic system of creation and destruction, with different regions moving in different directions. In some cases, the opening of a new ocean basin could lead to the closure of another. As plates rearranged themselves, the geometry of the system changed. The growth of the Atlantic, for example, was linked to changes in the Pacific and other ocean basins. The surface of the Earth is finite, and the movement of one part inevitably influences the movement of others. These global connections are reflected in the timing of geological events. Periods of rapid seafloor spreading in one region often coincide with changes in subduction and collision elsewhere. The breakup of Pangea was not just a local or regional phenomenon, it was part of a planet-wide reorganization of the plate system. The long goodbye also had implications for the deep interior of the Earth. As continents moved apart and new ocean basins opened, the distribution of mass on the surface changed. This altered how heat flowed from the mantle and how convection patterns developed below. Regions that had once been insulated by thick continental crust were now closer to the surface, allowing heat to escape more easily. In other areas, new thick crust formed as plates collided or volcanic material accumulated. These changes influenced where mantle plumes might rise and where future rifting or volcanism could occur. From the surface, some of the most visible signs of this phase were the development of extensive sedimentary basins along the new continental margins. Rivers carried vast amounts of material from the interior of the continents to the edges, where it was deposited in thick layers. These layers built up over millions of years, creating broad coastal plains and continental shelves. They also preserved detailed records of changing environments, including shifts in sea level, climate, and biological communities. Fossils found in these sediments often show a mix of old and new elements. Some species reflect the lingering connections of the supercontinent, while others represent new lineages that evolved in isolation after separation began. This blending of past and future is a hallmark of transitional periods in Earth's history. The climate of the planet continued to evolve as the land broke apart. The growth of new oceans increased the overall area of water on the surface, which helped moderate global temperatures. Ocean currents became more complex, with new pathways allowing heat to be transported in different ways. These changes likely contributed to shifts in global climate patterns, including periods of warming and cooling. The breakup of Pangea is associated with a general trend toward a more humid and less extreme climate in many regions, as the influence of the oceans expanded. At the same time, local conditions varied widely. Some areas became wetter and more forested. Others remained arid or developed new deserts. Mountain ranges continued to shape rainfall patterns and create rain shadows. The planet remained a mosaic of environments, even as the overall balance between land and sea changed. The long goodbye also left its mark on the distribution of resources. The formation of new basins and the reactivation of old structures influenced where minerals, fossil fuels, and other geological materials accumulated. For example, many of the world's major oil and gas reserves are found in sedimentary basins that formed along the margins of separating continents. These basins collected organic material in marine and coastal environments, which was later buried and transformed into hydrocarbons. Coal deposits, too, reflect the changing climate and geography of this period. Swampy coastal plains and river deltas along new shorelines provided the conditions needed for thick accumulations of plant material, which eventually became coal. These resources are, in a sense, part of the legacy of Pangea's breakup. They are the stored remains of ecosystems and environments that existed during this long transition from unity to separation. From a broader perspective, the long goodbye of a united Earth can be seen as a period of increasing complexity. The simple image of a single, massive land mass gave way to a world of multiple continents, diverse coastlines, and intricate networks of seas and straits. This complexity created new opportunities for life, new pathways for climate and ocean circulation, and new patterns of geological activity. It set the stage for the modern world, with its familiar arrangement of continents and oceans. Yet even as this transformation unfolded, the memory of the supercontinent was not erased. It remained written in the rocks, in the matching outlines of coastlines, in the shared fossils found on distant lands, and in the deep structures of the crust that still bear the scars of ancient collisions. These echoes serve as a kind of geological memory, linking the present to a time when the world was arranged very differently. They remind us that the shapes we see on a map today are the result of a long series of changes, not a permanent or final state. The long goodbye was also, in a sense, a long hello to the future. Each new ocean basin that opened created the conditions for new kinds of marine life. Each new continent that emerged as a distinct entity became a stage for unique evolutionary stories. The separation of landmasses allowed for the development of distinct biological regions, each with its own mix of species shaped by local conditions and histories. This diversity is one of the defining features of the modern world, and it owes much to the slow, uneven breakup of the ancient supercontinent. As the last connections between major landmasses faded, the world took on a form that would continue to evolve but would, in broad outline, resemble the arrangement we recognise today. The Atlantic continued to widen. The Tethys shrank and eventually closed in some regions, giving rise to new mountain belts. Australia and Antarctica parted ways. India began its long journey northward toward Asia. Each of these movements is a chapter in the extended farewell of a united Earth. Together, they trace the path from a single, sprawling landmass to a planet of many continents and wide oceans. This process did not mark an end to the story of continental movement. It simply marked a transition from one phase to another. The same forces that pulled Pangea apart continue to operate today, shaping coastlines, raising mountains, and opening and closing seas. From the perspective of deep time, the modern world is just another moment in this ongoing cycle. The continents we know are not fixed in place. They are still drifting, still responding to the slow flow of heat and material beneath the surface. As the long goodbye of Pangea settled into the new arrangement of land and sea, the planet entered a phase of history that is, in some ways, more familiar to us. It is the phase that leads toward the landscapes, climates and ecosystems we see today. Yet even in this familiarity, the imprint of the ancient supercontinent remains. It can be traced in the alignment of mountain ranges across oceans, in the distribution of certain fossils and rock types, and in the deep structures of the crust that guide modern plate movements. With these echoes in mind, the story naturally turns toward the present. What remains of Pangea in the world we see around us now? How can we recognise the fingerprints of that ancient unity in the shapes of continents, the patterns of life and the hidden structures beneath our feet? Look at a modern map of the world for a moment, not as a collection of countries or borders, but as a set of shapes resting in blue space. Even without any labels, there is a quiet familiarity in how some coastlines seem to mirror each other across oceans. The curve of eastern South America seems to answer the shape of Western Africa. The outline of eastern North America appears to echo parts of Western Europe. These visual hints are often the first way people encounter the idea that the continents were once joined. Yet these surface resemblances are only the most visible layer of a much deeper and more complex set of connections that link the present-day Earth to the time of Pangea. The echoes of that ancient unity are written into the planet at many levels, from the broad sweep of mountain ranges to the microscopic structures inside individual minerals. They are carried in the distribution of fossils, in the chemistry of rocks, in the patterns of earthquakes and volcanoes, and even in the flow of heat from the mantle. The modern world, for all its apparent separation and diversity, still carries the memory of being whole. One of the most striking geological reminders of Pangea can be found in the way mountain ranges line up across continents that are now separated by oceans. The Appalachian Mountains of eastern North America, for example, do not end neatly at the Atlantic coast. Their rocks, structures and ages closely match those of mountain belts in Western Europe and Northwest Africa. When these regions are placed back together in reconstructions of Pangea, the mountain ranges form a continuous chain, created by the same ancient collisions that brought those landmasses together. This continuity is not limited to one region. Similar connections can be traced between parts of South America and Africa, between Antarctica and Australia, and across many other pairs of modern continents. These matching geological features are like seams in a torn fabric, lines where the pieces still fit together if you know how to align them. The rocks themselves carry detailed records of these connections. Metamorphic belts, zones of intensely transformed rock formed deep within ancient mountain roots, can be matched in composition and age across different continents. The minerals in these rocks often show signs of having been subjected to the same pressures and temperatures at the same time, suggesting they were once part of the same continuous structure. In some cases, even the smallest details line up. Specific types of granite, formed from molten rock that cooled deep underground, can be found on both sides of an ocean, sharing similar chemical signatures and formation ages. These granites are often associated with the same ancient tectonic events, providing another layer of evidence for past connections. Beyond mountains and deep crustal rocks, sedimentary layers also tell a story of shared history. Certain sequences of sandstone, shale and limestone appear in similar order and age across now distant regions. These layers often represent ancient environments, such as shallow seas, river deltas or coastal plains, that once extended across what are now separate continents. When geologists compare these sequences, they can often match them like pages in a book that has been torn apart and scattered. The same fossils appear in the same types of rock layers, in the same relative positions on different continents. This consistency points to a time when those regions were part of a single, continuous landscape or seascape. Fossils provide some of the most compelling and accessible echoes of Pangea. The distribution of certain ancient plants and animals makes little sense in a world of widely separated continents, but becomes clear when those continents are reassembled. The seed fern Glossopteris mentioned earlier is one example. Its fossils are found across South America, Africa, Antarctica, India, and Australia. These regions now lie in different hemispheres and are separated by vast oceans, yet they share the remains of the same plant. This pattern reflects a time when they were all part of the southern portion of Pangea, connected in a way that allowed this species to spread widely. The same is true for certain ancient reptiles and amphibians. Fossils of animals that lived in freshwater environments and therefore could not have crossed oceans appear on continents that are now far apart. Their presence is a biological footprint of the ancient land connections. These patterns do more than just confirm the idea of a supercontinent. They also help scientists reconstruct how Pangea was arranged. By mapping where specific species are found and comparing their ages, researchers can infer which regions were connected and which were separated at different times. The echoes of Pangea are not confined to the surface. They extend deep into the earth, into the structure of the crust and mantle. Modern techniques, such as seismic imaging, allow scientists to create three-dimensional pictures of the interior of the planet by analysing how earthquake waves travel through it. These images often reveal large, dense structures deep in the mantle that are thought to be the remains of ancient tectonic plates that were subducted long ago. In some cases, these structures appear to correspond to the positions of ancient oceans that existed during the time of Pangea. For example, remnants of the oceanic crust that once lay between parts of the supercontinent may still be sinking slowly through the mantle, hundreds of millions of years after those oceans closed. These deep structures influence how heat flows within the Earth and can affect where mantle plumes rise and where new tectonic activity might occur. This means that the breakup and assembly of Pangea did not just shape the surface. It left an imprint on the deep interior that continues to influence the planet's behaviour today. The patterns of volcanism, the locations of some hotspots, and even the distribution of certain types of earthquakes may be linked, in part, to these ancient events. Another echo can be found in the way continents continue to move. The present-day directions and speeds of tectonic plates are not random. They are influenced by the arrangement of plate boundaries, the distribution of mass on the surface, and the structure of the mantle beneath. All of these factors were shaped by the long history of supercontinent cycles, including the formation and breakup of Pangea. For instance, the Atlantic Ocean is still widening. North and South America continue to move away from Europe and Africa as new crust forms along the mid-Atlantic ridge. This motion is a direct continuation of the rifting that began when Pangea started to break apart. At the same time, other parts of the world are experiencing convergence, where plates move toward each other. The collision between India and Asia, which began after India broke away from Gondwana, is still ongoing and continues to raise the Himalayas. This process is a later chapter in the broader story of how the pieces of Pangea have continued to rearrange themselves. The legacy of the supercontinent also appears in the distribution of natural resources. Many major mineral deposits, oil and gas fields and coal basins are associated with the geological structures and environments created during the assembly and breakup of Pangea. Coal deposits, for example, often formed in swampy regions along ancient coastlines and river systems during times when parts of the supercontinent lay near the equator. Today, these coal beds are found in regions that have since moved to different latitudes, but their presence reflects the past climate and geography of those areas. Oil and gas fields are frequently located in sedimentary basins that developed along the margins of separating continents. These basins collected thick layers of organic-rich sediments in shallow marine and coastal environments. Over time, heat and pressure transformed this material into hydrocarbons, which later became trapped in porous rocks and structural features created by tectonic movements. Even the distribution of certain metal ores can be traced back to the tectonic and magmatic processes associated with ancient collisions and rifting. The belts of volcanic and plutonic rocks formed during these events often concentrated valuable elements, leaving behind deposits that are mined today. The modern landscape itself carries subtle reminders of Pangea's influence. Large river systems often follow paths shaped by ancient structures in the crust. Valleys and basins can trace the lines of old rifts or sutures, even if those features are no longer active. For example, some major river valleys align with zones of weakness in the crust that date back to the breakup of the supercontinent. These zones, where the rock is fractured or thinner, can be more easily eroded by water, guiding the development of drainage networks over millions of years. Coastlines too reflect this history. The shape of many continental margins is influenced by how and where the land broke apart. Passive margins, formed by rifting and seafloor spreading, tend to have broad shelves and gentle slopes. Active margins, where plates collide or slide past each other, often have narrow shelves and steep coastal topography. These differences can often be traced back to whether a particular edge of a continent was created during the breakup of Pangea or shaped by later tectonic events. There is also an echo of Pangea in the way climates are distributed across the modern world. While today's climate patterns are influenced by many factors, including the current arrangement of continents, ocean currents, and atmospheric circulation, some long-term features reflect the legacy of ancient geography. The positions of certain deserts, for example, are influenced by the locations of large land masses and mountain ranges that affect wind patterns. The presence of major ocean currents, such as the Gulf Stream, is linked to the shape of ocean basins that formed as Pangea broke apart. These currents play a major role in moderating the climate of regions like Western Europe, making them warmer and wetter than they would otherwise be at similar latitudes. In this way, the ancient separation of continents continues to shape the everyday weather experienced by millions of people. Biology also carries the imprint of the supercontinent. The distribution of many plant and animal groups reflects ancient connections and separations rather than recent movement. This is especially clear in the southern hemisphere, where the remnants of Gondwana, such as South America, Africa, Australia and Antarctica, share certain biological similarities. For example, related groups of plants can be found across these continents, even though they are now separated by vast oceans. The same is true for some animal lineages, such as certain marsupials and ancient bird groups, whose distribution reflects the breakup of Gondwana rather than more recent dispersal. These patterns are studied in the field of biogeography, which looks at how the distribution of life is shaped by the movement of land masses, the opening and closing of oceans, and the formation of barriers like mountains and deserts. The story of Pangea is a central part of this field, providing a framework for understanding why life is arranged the way it is today. There is a more subtle echo of Pangea in the way scientists think about the future of the planet. The recognition that continents have come together and broken apart in the past has led to the idea of a supercontinent cycle, a long-term pattern in which land masses periodically assemble into a single large continent and then disperse again. Based on current plate motions, some researchers have proposed that a new supercontinent could form in the distant future, hundreds of millions of years from now. Different models suggest different outcomes. In some scenarios, the Atlantic continues to widen while the Pacific closes, eventually bringing the Americas into collision with Asia. In others, the Atlantic may begin to close, drawing the continents back together in a new configuration. These ideas are speculative, but they are grounded in the same processes that created and dismantled Pangea. The present-day world is not a stable endpoint. It is a moment within a much longer cycle of movement and change. The echoes of the ancient supercontinent can also be felt in the way the Earth responds to stress and strain today. Zones of weakness in the crust, inherited from past tectonic events, can influence where earthquakes occur and where new rifts might form. For example, some intraplate earthquakes, which occur far from active plate boundaries, are thought to be associated with the reactivation of old faults and rift zones that date back to the breakup of Pangea. These ancient structures remain embedded in the crust, ready to respond when stress builds up. This means that the deep past can shape the present in very practical ways, influencing where natural hazards are more likely to occur and how landscapes evolve over time. Even the chemistry of the oceans and atmosphere carries traces of this history. The long-term cycling of elements like carbon, sulfur and oxygen is influenced by the arrangement of continents and oceans. The formation of large land masses, the rise and erosion of mountain ranges, and the opening and closing of seaways all affect how these elements move between the solid Earth, the oceans and the atmosphere. The legacy of Pangea is therefore woven into the fundamental systems that regulate the planet's environment. It is part of the background against which modern climate change, ocean circulation, and biological evolution play out. There is a quiet continuity in all of this. The modern world feels fragmented, with its many continents separated by wide oceans. Yet beneath that fragmentation lies a shared history that still shapes how the planet works. When you stand on a mountain range in North America, you are standing on rock that has cousins in Europe and Africa. When you look at a fossil in South America, you may be looking at a species that once lived across a landscape that included what is now Antarctica or Australia. When you feel the ground shake in an earthquake, the fault that slipped may follow a line that was first formed when a supercontinent began to break apart. These connections can make the world feel both larger and more intimate at the same time. Larger, because the processes that shape it operate on scales of time and space that dwarf human experience. More intimate, because the place you occupy is linked, through a chain of events stretching back hundreds of millions of years to distant lands and ancient worlds. The echoes of Pangea in the modern world are not always obvious. They require careful observation, measurement and interpretation. They are found in the alignment of rock layers, the chemistry of minerals, the distribution of species, and the patterns of movement deep within the Earth. Yet once you become aware of them, it can be hard not to see them everywhere. The map of the world becomes more than a picture of the present. It becomes a snapshot in a long sequence, a frame in a film that has been playing for billions of years. As this perspective settles in, it naturally leads to a question about what comes next. If the modern world still carries the imprint of an ancient supercontinent, what imprint will today's continents leave on the future? How will the slow, ongoing drift of land and sea shape the planet hundreds of millions of years from now? If you let your attention drift forward instead of backward, past the familiar outlines of today's continents and into a future that stretches far beyond any human calendar, the surface of the Earth begins to look less like a finished picture and more like a scene that is still being drawn. The land you know is not settled into its final form. It is in motion, guided by the same deep forces that once gathered the pieces of Pangea and later pulled them apart. The question of where the continents may wander next is not about a single prediction. It is about understanding the patterns that have shaped the planet before and seeing how they continue to unfold. The first step in looking ahead is to recognise that the plates beneath the continents are still moving today. This movement is not theoretical. It is measured regularly using satellite-based systems that can detect shifts of just a few millimetres. North America is moving away from Europe and Africa as the Atlantic Ocean slowly widens. Australia is drifting northward towards Southeast Asia. Africa is moving gradually toward Europe. The Pacific Ocean is shrinking in some areas as its seafloor is consumed along long arcs of subduction. These motions, as small as they seem in a single year, add up over millions of years. At the scale of deep time, they become the steps of a slow global dance, one that rearranges the surface of the planet again and again. One of the clearest trends in the present-day system is the ongoing expansion of the Atlantic. Along the mid-Atlantic ridge, new oceanic crust is forming as magma rises and solidifies between the separating plates. This process pushes the Americas farther from Europe and Africa year by year. If this continues, the Atlantic will become wider, and the continents on either side will continue to drift apart. At the same time, much of the Pacific Ocean is surrounded by subduction zones, places where oceanic crust is sinking back into the mantle. This ring of fire, marked by frequent earthquakes and volcanoes, is gradually consuming the Pacific sea floor. Over long periods, this imbalance between creation and destruction means that the Pacific basin may continue to shrink. This combination of a widening Atlantic and a closing Pacific has led some scientists to suggest a future in which the continents around the Pacific, including the Americas, Asia, and Australia, eventually come together. In this scenario, sometimes referred to as Amasia, the landmasses would gather around the region of the present-day North Pole, forming a new supercontinent in the far future. In this vision, North America would continue its slow movement westward and northward, eventually colliding with Asia. The Bering Strait, now a narrow stretch of water between Alaska and Siberia, would close. The Pacific Ocean would largely disappear, replaced by a broad connected landmass. South America, moving northward, might also join this gathering, colliding with North America and contributing to the growth of a large continental block in the Northern Hemisphere. Australia, drifting north, could become part of Southeast Asia before being drawn into the larger assembly. Africa's role in this scenario is more complex. Africa is currently moving northward toward Europe, closing the Mediterranean Sea. This process, already underway, is slowly building new mountain belts in southern Europe. Over tens of millions of years, the Mediterranean may disappear entirely, replaced by a land connection between Africa and Europe. From there, Africa could continue its movement into Asia, becoming part of the same northern supercontinent. In this future, Antarctica might remain isolated near the South Pole, surrounded by ocean, or it might eventually be drawn into the larger landmass as well, depending on how plate boundaries evolve. Another set of ideas points in a different direction. Some researchers have proposed that the Atlantic, rather than continuing to widen indefinitely, could eventually begin to close. This would require the development of new subduction zones along its margins, allowing the oceanic crust to be consumed in a way similar to what is happening in the Pacific. In this scenario, sometimes called Pangea Proxima or Pangea Ultima, the continents that once separated from each other could begin to move back together. The Americas would drift eastward toward Europe and Africa. The Atlantic would narrow, and eventually the familiar outlines of the modern world would begin to resemble a new version of the ancient supercontinent. This kind of reversal is not without precedent. The geological record shows that ocean basins can open and later close over hundreds of millions of years. The Atlantic itself is relatively young in geological terms, having opened as Pangea broke apart. It is possible that, in the distant future, it could follow the same path in reverse. A third possibility focuses on the continued movement of continents toward the equator. In this model, sometimes called Nova Pangea, the land masses gradually shift into a broad belt around the middle of the planet. The Atlantic and Pacific both continue to widen and narrow in different regions, leading to a future supercontinent centered near the equatorial zone. In this arrangement, the northern and southern extremes of the planet would be dominated by oceans, while a massive connected landmass would stretch around the Earth's middle. This would create a world with very different climate patterns from those we experience today, shaped by the dominance of land in the tropics and oceans near the poles. Each of these scenarios is based on the same underlying principles: the movement of plates, the creation and destruction of oceanic crust, and the flow of heat within the mantle. What differs are the assumptions about how these processes will evolve in the future. One of the challenges in making long-term predictions is that the plate system is not perfectly predictable. The development of a new subduction zone, for example, can dramatically change the direction of plate movement. These zones often form along existing weaknesses in the crust, but the exact timing and location of their formation is difficult to foresee. The flow of the mantle also plays a role. Large-scale patterns of convection can influence the motion of plates from below, pushing them in certain directions or altering their speed. These patterns can change over time, adding another layer of uncertainty to any long-term forecast. Even with these uncertainties, there are some broad trends that can be traced forward. Africa's northward movement toward Europe is one. The continued northward drift of Australia is another. The general consumption of Pacific seafloor along its margins is a third. These ongoing processes provide a framework for imagining how the world might look in tens or hundreds of millions of years. The formation of a future supercontinent, whatever its exact shape or location, would have far-reaching effects on the planet. Climate patterns would change as the balance between land and sea shifted. Large interior regions would likely experience more extreme seasonal variations, similar to what occurred on Pangea. Ocean circulation would be reorganized, influencing the distribution of heat and nutrients around the globe. Life would respond to these changes in its own ways. New land connections would allow species to spread into regions that are currently isolated. At the same time, new barriers would form as oceans closed or opened, separating populations and driving evolutionary divergence. The rise of new mountain ranges during continental collisions would create new habitats and influence weather patterns. Rivers would carve new paths across emerging landscapes. Basins would fill with sediment, preserving the record of these changes for future geologists, if any are around to study them. The deep interior of the Earth would also be affected. The assembly of a large landmass would alter how heat escapes from the mantle. This could lead to changes in where mantle plumes rise, potentially triggering large volcanic events. These, in turn, could influence climate by releasing gases into the atmosphere. There is evidence in the geological record that the formation and breakup of supercontinents can be associated with periods of increased volcanic activity. These periods, sometimes called large igneous provinces, involve the eruption of vast amounts of lava over relatively short geological timescales. Such events have been linked to significant changes in climate and, in some cases, to mass extinctions. If a future supercontinent forms, it is possible that similar episodes of intense volcanism could occur, reshaping large areas of the surface and influencing the course of life on the planet. Thinking about these possibilities can make the present-day world feel more temporary. The continents you know, the oceans you see on a map, are not fixed features. They are part of a long sequence of arrangements, each one lasting for a time and then giving way to another. This perspective can also make the past feel closer. The story of Pangea is not just a tale of something that happened long ago. It is part of a pattern that includes the present and extends into the future. The same processes that brought that ancient world together and pulled it apart are still at work, shaping the planet beneath your feet. There is something grounding about that continuity. It suggests that the Earth is not moving toward a final state, but through a series of transformations. Each arrangement of land and sea is a chapter in a much longer narrative, one that does not have a clear beginning or end. The future paths of the continents will also be influenced by events that are hard to predict. The impact of a large asteroid, for example, could alter the balance of forces on the surface and in the atmosphere. Changes in the planet's rotation or in the behaviour of its magnetic field could have indirect effects on climate and tectonics. Even shifts in the distribution of ice and water on the surface can influence how the crust responds to stress. These factors add layers of complexity to any attempt to look far ahead. They remind us that the planet is a system of many interacting parts, not a simple machine that follows a single predictable path. Despite this complexity, the idea of a future supercontinent remains a powerful way to connect the deep past with the deep future. It frames the present as a moment between two larger states, a phase of separation between times of unity. From this point of view, the modern world is not an endpoint, but a midpoint. The continents are in the middle of their journey, having travelled far from the arrangement of Pangea and still moving toward whatever comes next. This way of seeing the world can change how you think about scale and time. Human history, with all its events and stories, occupies only a tiny fraction of the planet's timeline. The slow movement of continents, the opening and closing of oceans, and the rise and fall of supercontinents unfold over spans that make even the longest civilizations feel brief. Yet those human stories are still part of the same world shaped by these deep processes. The mountains that influenced where cities were built, the rivers that guided trade and travel, the climate patterns that shaped agriculture, all have roots in the long-term movement of land and sea. In that sense, the future of the continents is not completely separate from the present. The choices and experiences of today's world are happening on a surface that is already on its way to a new configuration. There is also a quiet sense of wonder in imagining these distant futures. It invites you to picture landscapes that no one has ever seen, oceans that do not yet exist, and mountain ranges that will rise in places that are now plains or seas. In one possible future, the site of a modern ocean might become the heart of a vast interior desert. In another, a quiet coastline might be pushed high into a mountain range. Forests might grow where ice now lies, and ice might cover regions that are currently warm and green. These are not just speculative images. They're grounded in the same kinds of changes that have happened before. The Earth has already transformed itself many times over. There is no reason to think it will stop now. As the continents continue their slow wander, they carry with them the memory of where they have been. The rocks beneath them preserve the record of ancient oceans and long-vanished mountains. The shapes of their edges hint at past connections and separations. Those memories in turn shape the paths they take forward. Old faults can guide new rifts. Ancient sutures can influence where future collisions occur. The past is not just behind the present, it is built into the structure of the planet, influencing what comes next. This layered sense of time and movement can add a different kind of depth to a simple act like looking at a map or standing on a piece of ground. The land is not just a place, it is a traveller, part of a long journey that began long before humans appeared and will continue long after. The story that began with a question about how a single ancient landmass came together ends, for now, with a question about where today's world is headed. The answer is not a single destination, but a range of possibilities shaped by forces that operate far below the surface and far beyond the span of any one lifetime. As those forces continue their work, the continents will keep drifting, colliding, separating, and reuniting in new ways. The world will keep changing, not in sudden leaps, but in the same steady, patient motion that has carried it through billions of years. And in that ongoing movement, the memory of Pangea remains, not just as a chapter in the past, but as a reminder that the planet you inhabit is part of a much larger, continuous story, one that is still being written, layer by layer, mile by mile, across the face of the Earth.